Hey guys, welcome to Gym Term 2A walkthrough. Apologize for getting this out so late. Although many of you are probably going to study over the weekend anyway, so maybe this might actually be the best time to have uploaded this. It was just a bit busy this week. I'll definitely get out another one, so I'll get this one done and then I'll get out another one for the second midterm, but I won't have time to do the third. And the fourth one that I'm like writing that I'll also get out tonight. Yeah, I just don't have any time. I have like other for 118C, I also have to build their exams and make their reviews. So not enough time, unfortunately, and everyone's exam is next week. So just doing the best that I can. But don't worry, right? The first two midterms should cover most concepts, if not all, that you need to do very well, at least to pass in the class. And that's the goal, right? Is we want to be able to pass. So yeah, so I'll definitely get out 2 videos. Definitely get the second one done tomorrow. And I'll upload it, and then I'll have the keys out. Don't worry, I'll get the keys done, have them out. This one, this key will come out with this video tomorrow. I'll get all the other ones done, and then we'll call it a day. I do have one more exam that I'm writing. I just haven't gotten, it's like it's that weird medium of like I have enough problems to ask questions on, but I'm not sure if I should just make another one with more problems. But anyways, I'll get that out. I'll get that done. Get that squared away, and then we can have a great time studying. So. That's the current plan. As with every 2A video or every A video, right? There's always a bit of a review at the beginning, so we'll start with that just so we are all very familiar with what to do. Although I will admit I don't want this video more than 2.5 hours long, so I'm really looking at the clock today, and going to be very, very on time. So in order to meet those constraints, I think that only leaves me about an hour and a half to do review and then an hour to get through this exam, which will probably be enough time. Probably won't need the full hour, but want to get through review through an hour and a half. So I'm going to put emphasis on other things more than others. So for example, diene additions, diels, alder, benzene substituent effects, those are where we're going to give priority. Other things, not so much. So we might not talk about aromaticity. We might not talk about allylic stuff. Probably not even going to touch electrocyclics. But that's okay, because if there's any concept on here that we need to know, I'll go over it really quickly, right? For example, C is an aromaticity question, so we'll have to talk about it anyways, and B also has an aromaticity element to it. And actually, so does D. All 3 of these are aromaticity questions. And then there's a couple questions on here, right? Like the electrocyclics or F or D, right? We'll get to those concepts when we need to. But yeah, I just want to be able to make sure this video is manageable and not like a complete throwing of material in your guys' faces, right? And I also don't have that much time, right, to make 3-hour videos. So 2.5 hours is the goal. So I'm watching the clock like a hawk today. But yeah, cool. So with that being said, let's just get into it. The review. Okay. Again, we're going to emphasize certain things over others. And I'll make sure I'll let you guys know what it is I'm skipping over that you should make sure to know. Okay, cool. All right. So chapter 14, beginning of the class, we talked a lot about alkenes, right? And their role as nucleophiles towards electrophiles, right? So classic attacking a proton, forming a carbocation. But the other thing about alkenes is that, they're pi bonds, they have p orbitals, pi electrons, that we could potentially conjugate with an adjacent p orbital. So for example, let's say I go ahead and throw a cation on this thing. And now suddenly I have these 3 p orbitals next to each other, right? Back in 118A, we kind of asked you guys to accept that 3 p orbitals next to each other, right? They're going to mix together, conjugate, and resonance is going to occur, right? Delocalization of electrons. But we never really sat down to talk about why we should do that or why should we expect that, right? Why is it that p orbitals want to mix to make these molecular clouds rather than just staying localized in their bonds? And probably the best way to explain it is to look into molecular orbital theory. So I know this is not everyone's favorite part, but trust me, it's not as bad as you think. And there's only a couple systems you have to understand. And if you can understand those, you'll do well on those questions or questions related to those, okay? So if I take these 3 p orbitals and I mix them together, a little bit of orbital math. You add 3 orbitals in, 3 orbitals have to come out. Okay, so I get these 3 p orbitals here. Okay, oops, sorry. Actually, let's do this. We put them down here. Okay, so we have 1 molecular p orbital right here. Okay, we have our second one here. Okay, then we have our third one up here. Okay, so we have 3 molecular p orbitals, and these are all a function of, these are all increasing in energy as we go up. So I'll write that in. Okay. So why is it that our p orbitals, right, want to mix to make these molecular p orbitals? Okay. Well, if I fill in the electrons from this pi bond here, right? They're going to go down here. So there's 2 pi electrons in that pi bond. So 2 of them are going to go right down there. Okay. That leaves us with 2 electrons that would have been at a degenerate level, right? That would have been at a standard level in a lower state. Right now they're at a lower state. So by conjugating, immediately 2 electrons experience the effect of being at a lower energy. And that's what systems want to be, right? They want to be as lower energy as possible. So by all means, I mean, we should be convinced, yeah, definitely there's going to be conjugation in this system, okay? Or any allylic system or p orbital system, we will see this type of conjugation. Okay. Now for the other 2 p orbitals that I haven't really drawn out, it's pretty simple figuring out how to draw p orbitals. The main idea is that the bottom state's always the ground state. It's always everything's in phase. And then everything above will always add an orbital, a node. So for example, this second state here will add a node. A lot of you might be wondering whether the node adds there or adds here, right? The general idea is you want a symmetric node. So for these odd systems, especially on that first jump, right? Actually, the node's gonna be right down the middle like that. So instead of having an orbital here, right, that can accept electrons, we actually have a node down the middle. So that means that these phases must be not matched. Okay. The highest system is always very simple, right? In this case, there's only, we're going to add 2 nodes now because we're going up another level, but this is the highest possible system. So highest possible orbitals, molecular orbital always has the maximum number of nodes. So we can go ahead and put these guys in here like this. Okay. Cool. And you can see all the nodes are not matching. Now we do have names for these. We call these like bonding, non-bonding, and then anti-bonding, right? Most of you should remember from Gen Chem, bonding is sort of the good orbital, right? That's electrons promote bonding if they're put into this orbital. Non-bonding has absolutely no influence, and anti-bonding is the bad orbital, right? Because it promotes destruction of the molecule, degradation of those bonds, okay? So generally, we want electrons in the bonding. Non-bonding is fine, no problem with that. We want to avoid putting electrons here in the anti-bonding, okay? Cool. Now we'll see how to do the 4 electron system very soon, especially for diels alder. We'll see how to do this, and then we'll very briefly talk about the 6 electron system. Sorry, 6 electron system. And actually, if we wanted to, we can even talk very quickly about a 5 electron system, or a sorry, not electrons, 5 p orbital is what I wanted to say. Sorry. So 4 pi orbital system. 6 pi orbital system, and then we can look at a 5 pi orbital system as well. At least we'll see those moving down the line. Okay, cool. All right. So if electrons are being lowered energy, very likely the system will conjugate just because it wants to have that lower energy state. Okay. And so allylic systems in general, right? I mean, especially if we think about electron-wise, are going to be a lot more stable and a lot more reactive towards certain reactions than their non-allylic components. For example, let's say that I have these 2 bromides and I want to transmetallate them to form the anions, right? So essentially I'm forming the Grignard anions here, okay? You could imagine, right, this anion, not so bad, right? It's not terrible to form, but the allylic version of this is going to be a lot easier to form simply because we have that resonating system possible, okay? This is actually so much so better that even the vinyl system loses out here. Let's say that I have a vinyl system. So I have right on the alkene, the anion, right? The allyl system is a lot more stable than that. Some good values to know is 50 for the alkane, 45 for the alkene. And then for the allyl, it's about 40. So it's a very big difference there. It's definitely a lot more stable than you would think, okay? Alkyne still sweeps this though. Alkyne is still a lot more stable at a 25. So it's not crazy stable, right? But it's a lot more stable than you would think. Usually we expect sp2 carbons to be much more stable than sp3, but this sp3, sp2 carbon, a lot better, right? Because it has the ability to resonate, okay? On the other hand, let's say that I took this guy and I try to do an SN2, SN1 type reaction. So SN1 type reaction, well, first off, this would have absolutely no product, right? If we try to do an SN1 type reaction, because the carbocation intermediate, incredibly unstable, right? It's a primary. If anything were to happen, it would have to be via some kind of hydride shift, like an instantaneous hydride shift as well, right? So like this would have to move over, but that's really hard to promote. So we almost consider this not to work at all. But if we try this reaction with the allyl, we definitely see an SN1 type reaction occurring. Okay, and that's because this cation, despite being primary, is able to resonate. It's able to resonate. So primary cations finally have the ability to exist as long as they can resonate with a pi bond, as long as they're allyl. Generally speaking, for cation stability, right, if I wanted to rank them, right, primary is absolutely the worst. Oops, sorry. Primary is absolutely the worst, followed by secondary, followed by allyl. So when we say allyl, we are specifically talking about this 3-carbon system, followed by tertiary, and then substituted allyl. So what does substituted allyl mean? Substituted allyl means just a allyl system with more carbons attached to it. So for example, if I had this system here, right, that's more stable than tertiary, especially if this carbon is tertiary as well, right? If I have this system here, right, that's substituted allyl. So it's a bit more stable, right, than the tertiary, because tertiary, secondary, primary, all they have is hyperconjugation. Allyl has hyperconjugation and resonance, right? So it's that double effect. Now, every year I get this question, why is it that allyl is worse than tertiary if allyl has resonance? It's because allyl is still a primary cation. Don't forget that. Allyl is still primary, right? If we even look at the resonance contributor, that's still a primary cation on the other side. So 2 primary cations don't have the ability to overcome a tertiary, but they do have the ability to overcome a secondary, right? So they're still more stable than a secondary, but not quite there yet with the tertiary. But once we substitute it, a lot more stable than the tertiary. Okay, cool. All right. So carbocation wise, right, we have a lot more stability. We can also then look at radicals. So let's say that I wanted to do a radical reaction, as well, as you guys will learn with NBS or have already learned with NBS, right? We can go ahead and form stable radicals as opposed to on this sp2 center or even on an sp3 center. So all those radical halogenations that you guys want to do, make sure you account for any allyl position, because that position is going to be the fastest. It's going to be definitely the easiest position to brominate via the allyl radical. Okay, cool. So allyl systems, right? Conjugated systems. This thing you have to look out for, right? Is there a way that I could draw an intermediate that's conjugated, and can that help me figure out what the problem is or what the product is, right? What stability does this system bring to us? And that's kind of the name of the game. So when you're doing your practice problems and when you're doing your, when you're doing the practice exams, right? For example, I'm going to just spoil one of these. This is one of the questions I wrote on one of the exams. When you see something like this, again, you see a nucleophile and you think, okay, I have a bromide secondary, maybe both are the same, blah, 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 something. Remember, think in context to the chapter, right? Is there anything different here that could potentially help drive or help me think about what is actually going to happen? And I see a pi bond here and I think, okay, chapter 14, all about that allyl system. This is allyl and this is not. So if I had to put my money on it, I'm guessing the allyl guy reacts. The non-allyl guy does not. Okay, cool. All right. So for the sake of time, I'm just going to call it there on that. And we're going to move into dienes, which again, dienes are just if I take that allyl system and I decide, hey, let's just go ahead and pop an alkene on there. And so now we have not only we have 3 p orbitals, we have a 4th one now, right? And for diels alder, we'll talk about what the molecular orbitals look like, okay? But again, if we have these 4 orbitals next to each other, we have conjugation. And so this system is going to act a little differently than a normal alkene, right? In the case that a normal alkene, right, we just follow Markovnikov's rule, or we just follow, just stability of the cation. I guess we still are following that, but to a larger degree, right? Because if I think about the 2 cations that could form from the protonation of this diene, I guess part of you guys might be thinking, okay, right, obviously this cation can't form because it's primary. This one's secondary, but keep in mind, really the most important thing is that it's secondary and it's allylic, right? Because imagine if I just did that. If I put a carbon there and now suddenly these are both secondary. Again, using the idea of conjugation, it's so much better than we think it is, right? That cation is definitely going to be way better than the cation right there. Okay, cool. So generally with these diene additions, the hydrogen or the electrophile, whatever it is, will usually add on that one position to form a allylic cation, and this allylic cation, right, is going to resonate with the pi bond to have these 2 representations. Okay, so we have a secondary and we have a primary cation. Now, in reality, right, it's actually much more correct to represent this cation as a hybrid, right? To say that this cation is delocalized across the system, and we'll talk about why that's important in a second. But this is the most accurate representation. Now, looking at this representation, you might be thinking, well, it looks like this cation you're showing is spread across 3 carbons. So possibly a nucleophile can attack from all 3. But there's two things that can help you combat that thought, right? One is that when we look at the actual resonance contributors, we can see that the charge is really, spread across 2 carbons, right? Or at least it's present on 2 carbons. Okay, so it's definitely going to be on the terminal ends of the allyl system. Another thing we can do is we can look at the orbitals for that allyl system, right? Because this is an allyl system, right? And notice that the orbital in which the nucleophile will add electrons in is going to be this non-bonding orbital, where if we look very carefully, there is a node down the middle. So the middle of an allyl system is always off off limits. It's never going to attack, even when we draw it in the resonance hybrid form. We're only ever going to get attack on the ends there. Okay. But anyways, right, a nucleophile could potentially attack on this carbon here, which leads to this secondary substituted product, right, with this monosub pi bond, or we could end up with this primary substituted product with this more stable internal disub pi bond. And so again, the question becomes, which one is the correct answer, right? Which one do I want to put on my exam so I'd always get this right? Obviously there is arguments for, hey, this is a secondary cation versus a primary. So this is clearly more stable, right? That's a more stable cation right there. Right. On the other hand, right, when I look at the product, say, look at that. This pi bond is not that stable, but this one is definitely more stable. So this is a more stable. We could say pi, or we could just say product, just to speak generally. Okay. So who wins, right? Who is the one that matters more? Turns out that both can potentially be great reasons for why we get either product. And really what it'll depend on is our time scale, is our condition, right? This is the introduction to kinetic and thermodynamic conditions. Okay. Now, kinetic, as the name might suggest, right? Kinetic, very fast, right? Kinetics concerns the fastest forming product. So we're thinking fast here. What forms first, right? And usually what that means is we're talking about a stable intermediate. Okay. So the more stable the intermediate, the easier it is to form, right? The lower level of energy is required to form that intermediate. So when I look at these 2 intermediates, these cationic intermediates, I see this more stable cationic secondary position versus this primary one. And I think, okay, this guy is easier to form, right? I don't really need a lot of energy to form that secondary cation as opposed to this primary one, right? So kinetically speaking, right, in the beginning, when we are protonating this diene, right, very, very easy for the resonance hybrid to carry a lot of influence on that secondary position. So a lot of emphasis on, hey, this position is much more stable. So a lot of the cationic characters is buried on that carbon. And so when we're talking fast, so low time, right, and low temperature, right, is a delta here actually. So low time, low temperature, right, this is going to be the cation that's captured most of the time. Okay, so kinetically, the more stable cation is what's going to be captured. Okay, now remember, this is kinetic product, so only the intermediate stable. We're not really looking at the product just quite yet, right? We can see here that clearly the product is not that stable because it is a monosub pi bond versus here is a disub pi bond. So thermodynamics considers, hey, what if I just let this sit for a little bit? So this is a bit slow, but let's just let it sit for a little bit, right? So we give it a lot of time, right? Maybe we give it a little bit of a heat massage, right? And we kind of allow it to relax itself into its most stable form, right? That is what thermodynamics is. So this is when we concern ourselves with the more stable product. So thermodynamic product is going to be the one with the better pi bond, or the more stable pi bond. Okay. Now, generally speaking, obviously, we don't really talk about time on exams. So when we want to denote kinetics versus thermodynamics, we normally talk about temperature, right? 0 C usually. So anything below room temperature is what we consider a kinetic condition. Okay. Usually anything above 25 C is what we consider a thermodynamic. So good values for these are like 0 or like 80, right? If you see either one of those, you know pretty clearly which one we're talking about. Okay, so all these diene additions, whatever you're adding across of it, right? Whatever the electrophile is, whatever the pi bond addition is, all you really have to think about is, am I in a kinetic condition or am I thermodynamic condition? Because if I'm kinetic, then the only product that will ever form, or I'm allowing to form, is that first product, right? That one that goes to that most stable intermediate. So I'm only really allowing this guy here to form. But if I'm going for a thermodynamic condition, then what I'm saying is, okay, I'll let this guy form, but then I'm going to let it sit there and think about what it just did, right? Think about its actions. Think about if it's happy where it is. And 99% of the time, it's not really happy where it is. So it reverses and it goes through the thermodynamic intermediate, right? That less stable intermediate to form ultimately the more stable product. Okay. So it's all a temperature game, and it's all of a, cation versus pi bond game. Okay, cool. So we'll go over two examples that are pretty good examples of exemplifying the whole thermodynamic versus kinetic product. This first example is isoprene. It is an asymmetric diene, so it is going to matter where we protonate, right? That previous example was not symmetric. So this was not a symmetric at all, so it didn't matter. Sorry, this was symmetric, is what I meant to say. This is a symmetric system, so it didn't matter who I attacked, but now it is going to matter, and this is really the question that's asked on the exam, right? But I'll take isoprene, and we'll consider what happens when we protonate across this pi bond, right? And then what will happen when we protonate across this pi bond. Okay, cool. So I'll draw these ones down here first. Not because it's correct. I actually don't know if it's correct just yet. I'm just choosing to draw these first. Okay, so these are our two intermediates here. And then I can draw the orange intermediates, this versus this. Okay, cool. So we have 4 intermediates here, and maybe some of you guys are freaking out like, damn, do I got to draw 4 intermediates every single time and then do some kind of analysis? No, you don't. Because remember, we are talking about kinetics and thermodynamics, where kinetics always occurs first. So it's always the fastest forming thing, right? Kinetics will always dictate your first product or your first set of intermediates. So when you're considering which pi bond to protonate, your question really becomes kinetically, which pi bond is going to react faster? Kinetically, which pi bond will give me the better set of carbocation, okay? Or the more stable carbocation. So your job is to look at all these carbocations and ask yourself that question: which one is the most stable? As you can see, this is secondary, this is primary, this is tertiary, this is primary. Easy, right? There's a tertiary right there. So we are never going to consider the protonation across that pi bond. Okay. In fact, it never happens, because kinetically, the first cation to form is going to be this tertiary cation here. Okay. And so when that cation forms, right, again, we can get 2 possible products. So we get this, and we get this here. Actually, let's actually use a specific source, because I want to use specific examples. Let's say HBr, and then we'll say this is 0C, and this is ADC. Oh, I guess I accidentally gave it away. I should have, my bad. But okay, that just means Br minus is going to attack here. So we'll add here, and we'll add here. Okay, cool. So again, when we're considering which one is thermodynamic and which one is kinetic, right, it's a question of cation versus pi bond, right? I look here, tertiary versus primary cation. This tertiary cation is clearly more stable, and so therefore it's going to add up that carbon there. Okay, and this is going to be the kinetic product. Okay, cool. When I look at this one here, it's primary cation, but I have a pi bond that's highly substituted. So this is clearly going to be our thermodynamic product. So this is at ADC. Okay, cool. And that's all it takes. So isoprene, right? How do you identify isoprene type problems, right? Because obviously we're not going to see isoprene all the time. The best way to identify an isoprene is if you kind of count this 1, 2, 3, 4, right? You'll notice that the most substituted carbon is on a 2 carbon. So I like to call 2 and 3 the kind of quote unquote internal carbons, and I call these 1 and 4 the external carbons. When your more substituted carbon is an internal carbon, so a 2 or 3 carbon, right? This is sort of the pattern that you end up seeing, right? Where the pi bond that attacks is the one that's more substituted. Because when we do that attack, right, we always get the initial cation on that tertiary center. Okay, so a little trick there, little insider tip, right? If you can see what I'm saying, in that when you have these internal carbons that are more substituted, it's always the carbon that it's always the pi bond that is touching that more substituted carbon that is going to be the fastest to react. So you can even see in this example here, right? This will, I mean, you can draw the other ones if you wanted to prove it to yourself. It's up to you, but this is going to be what we get. Okay, and so you can clearly see, right, kinetic versus thermodynamic right there, just like that. Okay, cool. So that's isoprene, and isoprene type dienes will react as such. Okay. Now we can also have another type of diene. So hopefully you guys will understand if I draw here, what I'm changing here, right? Remember, we talked about 2, 3 having the more sub position. Now it's like a 1 or 4 that has a more sub position, if that makes sense. But again, we'll ask that same question, right? Which position is going to pronate first? So I'll pronate on this side. Sorry, I'll pronate this for this side, right? Just like I did last time. And maybe some of you are already like, oh yeah, I see where this is going. Maybe I don't even need to listen to the explanation because I'm just that smart. I don't even need to explain to me. I know where this is going. That's totally fine. That, I actually hope that you guys are feeling that way because it means that you're more prepared than you think you are. Okay, cool. So if you want to, you can pause and think about this. And if you don't want to think about it, just keep on listening. But again, let's say that we're doing like H plus H2O, or actually I'll do this because sometimes it shows up D plus D2O. So deuterium, yuck. I know we hate deuterium, but remember that just means we have to show the hydrogen, right? Or the deuterium in this case. So I'll just draw in the deuterium. I'll be a little consistent with how I draw it, but we just got to draw it in. Okay, so don't forget that. This is probably the easiest thing to mess up on accident, even though you totally understand the question. Okay, we draw in the deuterium, right? When the water goes to add in, or I mean, even before it goes to add in, right? One of these cations is going to dictate which resonating set is better. So again, answer that question. We have a secondary, primary, maybe that's good. Secondary, tertiary, oof, yeah. Absolutely no way are we ever going with the more subset. Okay, or sorry, the more sub pi one attacking first. Okay, it's always going to be this far right one that attacks. Okay, cool. And again, if you want to think about it, right, it's like that external outside type carbon 1 and 4. Those are, when that is more substituted, then it's always the other pi bond that attacks because it allows you to form that cation at that more sub position. Okay, cool. Anyways, and so again, we can ask ourselves when D2O attacks, right? And I'm going to skip the protonation here. So before anyone, yells my ear off, hey, did you mean to draw this this way, blah, blah, blah. I'm just skipping the protonation. Okay. But you can get 2 possible products here. Okay. One like this and one like this. And again, the question becomes which one's kinetic and which one's thermodynamic. And shouldn't be too difficult to choose here, right? We're just looking at cation versus pi bond. But this cation definitely going to be kinetic, so it's going to form the fastest 0C, or it carries the most character, right? So it carries the most character, right, in the resonance hybrid. So at lower temps, at a higher, at a lower time scale, right, the water is going to attack the side with the higher cation character, right? Versus give it some time to think about it and it realizes, wait a minute, maybe this is not our best possible arrangement. So it reverses, and then we go towards here to down here. Oh, sorry, not the other way. My bad. So it reverses, goes this way and this way. That's what I meant. Cool. All right. So again, how can I identify this on an exam? Again, it's like as if I took that first example that we talked about, but now we have a 1 or 4 carbon that is, more substituted. And so in this case, always you will see the cation forming here because that puts it in direct conjugation with that tertiary carbon. Cool. Now, I imagine a lot of you guys are going to do some external research, which is very good. The more research you do on your own, the more you learn. And you're going to find a lot of different answers for how to do these and a lot of different things. I'll just tell you guys something right now. Every professor has a different way of teaching this and doing these problems. This is just in a series way of doing it. In fact, actually, this is incorrect. It's not always like the whole cation thing and then pi bond thing. That's not always the most correct thing to do. But it is just the way it's been taught at the school since forever. Some of your friends that might help you guys study, or maybe some of the peer tutors too, or even the AATC tutors might teach you a different way. And that might be just because they learned it from like Dr. Helix, for example, who teaches it differently from Dr. Nasseri. So just be very careful what source you use. Just make sure the source understands what Nasseri is teaching. She kind of has, again, every professor has a different way of teaching this, and this is just her way of doing it. And I'll tell you right now, it is different from Dr. Helix's way. It's different from Dr. Lieben's way. Everyone teaches it their own different way. So it's a bit of a headache. But I can, just make sure if you're gonna look at outside resources or if you're gonna consult with outside persons, make sure they know that you're taking it with Dr. Nasseri so they can advise you correctly. You can even, if you look at the ATC sheets too, I think Maria has it like completely just littered with, this is for Helix's class, this is for Nasiri's class, blah, 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 right? Because everyone does it differently. In fact, everyone's just wrong. There's a little spiel, but I was recently reading, I'll put it in the Discord, but there's actually, this is not even the real mechanism for Dienes. It's still being investigated. A couple of years ago, a paper came out where they were investigating a possible mechanism for this using computations. And actually the mechanism for this is not as discrete. I mean, it's not as simple as just cation forms and things add to it. It's the same thing with alkynes. With alkynes, we tell you guys alkynes are like electrophilic additions. That's also a lie. The thing is, no one's ever going to sit down and rethink this because for the most part, we can predict this 90% of the time correctly. Sometimes it's wrong, but most times correctly. So no one bothers to actually sit down and figure this out. There's also no money in mechanism work like this. So don't stress out, just know the tricks and you'll be fine, okay? Cool. So that's diene additions, and we'll call it there just because for time's sake, because now we need to spend the majority of the hour on the most important diene reaction of the quarter, and that is the diels-alder reaction. Okay. So the diels-alder reaction involves a diene reacting with an alkene in a way that we've never really seen before to form a cyclohexene. And so looking at this, it's not very clear instantly how this reaction even works, because we don't really see a nucleophile and an electrophile, right? Like when I look back here in the diene additions, I can clearly see D plus D2O. I know what is reacting. Like this is the electrophile, right? This is the nucleophile, and then this is the nucleophile. This is the electrophile. It's really easy to make that call. But when I look at the diels-alder, what in the world, right? Like what is going on? I have no idea. At least looking at it initially, who is the nucleophile and who is the electrophile. So the diels-alder is truly the first reaction. It's a cycle addition. We call this a 4+2 because there's 4 pieces here, 2 pieces here. So this is a 4+2 cyclo addition. But this is the first reaction of its kind that you guys will learn that is completely controlled by orbitals. Okay, it's completely controlled by orbital interactions. So to understand this, we got to look at the orbitals. So let's go ahead and let's look at our orbitals. Again, like I mentioned, we will be looking at many different pi systems. So we'll be looking at the 4 pi system as well. Okay, we have a 4 pi system here. Again, 4 p orbitals go in, 4 will come out, 4 molecular will come out. And this one is a bit easier to set up than the 3 pi because there's no weird like node through the, an orbital. Very, very simple, right? Again, remember ground state, everything's always in phase, okay? And then we have a second state where we have a node, we need a symmetric. This is not symmetric, but this is. So we can have, for example, these in phase and then these are out of phase, okay? Now we have to add in 2 nodes in a symmetric fashion. That's gonna be our symmetric fashion, okay? So remember, across a node, things are out of phase. And then remember, the highest one is just as easy as the lowest one because all you're doing is adding the maximum number of nodes. Okay, so here we go. Those are our pi orbitals for butadiene or 4 pi system. Okay, and so we have 2 pi bonds, so that's going to be 4 pi electrons. So we can go ahead and fill in 4 pi electrons, and we can go ahead and we can see that it's this second orbital that's full, and then this third orbital that's not full. Okay, and we have terms for these. The highest orbital, the highest molecular orbital with electrons in it, we call the HOMO, or the highest occupied molecular orbital. Okay, and then this or above it, always above the HOMO, is going to be what we call the LUMO, which is the lowest unoccupied molecular orbital. Okay, now if you talk to theoretical chemists, if you talk to grad students, they'll probably tell you this, or you can say this to them and they'll probably agree. Every single organic reaction can be boiled down to the single sentence of the HOMO reacts with the LUMO. Okay, the HOMO of some nucleophile, it gives electrons to the LUMO of some electrophile. Okay, that's basically organic chemistry in one sentence. Okay, now again, obviously the diene's not reacting with itself, so it's not like you're doing a HOMO-LUMO reaction with itself, but we are doing a HOMO-LUMO reaction with the diene, or sorry, the alkene, which we call the dienophile. Okay, which that's just 2, it's 2 p orbitals right there, so 2 pi system. So very simple to draw these orbitals here. So again, ground state has zero nodes. The top state always has the maximum number of nodes. In this case, that's only going to be 1. So this is the simplest system you can know. Okay, and so again, we have 1 pi bond. So we're going to have 2 pi electrons. Again, this is our HOMO, and this here is our LUMO. Okay. So like I mentioned, right, in this reaction, and generally any reaction, all it is a HOMO-LUMO interaction. But not only is it a HOMO-LUMO interaction, but it's a HOMO-LUMO interaction between orbitals that are symmetrically that are symmetric, right? They are the same. They have the symmetry to react with each other. Okay. So what does that mean? Well, if I look at the atoms that are reacting, so these green carbons here, and then these blue carbons here, right? That would be, for example, if we're looking at the LUMO of the alkene, right? That would be these 2 carbons here, right? On the diene, that would actually be these 2 carbons here, right? The outside carbons. I'll mark these guys just to help you guys see it, but these guys would just be whatever. They're just in the middle. They're not interacting as such, right? They're not doing anything, at least primarily. But we can see here. Oh, sorry. So if this is the LUMO, then we should look at the HOMO of this guy. Okay. But if we look at the HOMO and the LUMO, right, symmetry would mean that we have matching orbitals. So for example, if I call this A, orbital A, where the top lobe is not shaded, bottom is shaded, I can see here there is a matching orbital A. And so those two can't interact, right? If I look over here and I call this B, right, where the top is shaded in and the bottom is not, I see that there is a matching orbital B. Because we have this symmetry, we have this congruency on the interacting orbitals, this reaction is symmetry allowed and is what drives the cycle addition forward. Okay, so the reason why we're able to have this reaction is, 1, we have a HOMO-LUMO interaction, but 2, we also have symmetry agreements or symmetry congruence, right? There's symmetry between the orbitals interacting, and therefore an interaction can happen. Okay. Now, I kind of assume that the HOMO was the diene and the dienophile, the alkene was the electrophile. And that's just because that's just normally how we view it. I mean, if we kind of flipped it on its head, you would see that it wouldn't matter. Like if I treated this HOMO and I treated this LUMO, and I kind of looked at, who is sending electrons to who, or if I look at orbital symmetry, it's there. So you can see that these orbitals, right, are the same as these orbitals here. So the symmetry is there. It is available. But right, generally speaking, we tend to see our diene as the nucleophile and the dienophile as the electrophile. So this is usually our nucleophile, okay? And this is our electrophile. And as such, we can modify these 2 groups to contain groups that make this more nucleophilic and make this more electrophilic, okay? Okay, but again, right, understand how to draw these molecular diagrams. This is something that can be asked of you on the exam, by the way. You can be asked to draw the HOMO of the diene. You can be asked to draw the LUMO of the dienophile. You can ask to draw the LUMO of the diene, right? You should be very comfortable with drawing these molecular orbital diagrams. Okay, cool. Now, usually accompanied with this explanation of the diene reaction is every single reaction just allowed to do this? Are we allowed to just combine 2 pi bonds whenever we want, or 3 pi bonds whenever we want, just because we see them? And the answer is no, right? Because we have to make sure that there's symmetry. So for example, why is it that we don't talk about the cycloaddition of 2 alkenes to make a cyclobutane, right? Why is it that we can't just do that? And so again, if we kind of look at the orbitals here, luckily we've already done the orbital work, so we already know what they look like, and it's not particularly hard to do this. Okay, cool. So that, right? And then these are in phase, right? Again, if I look at my orbitals here, right? One of these guys is going to be the HOMO, the nucleophile. The other is going to be the LUMO, the electrophile. When I look for that symmetry congruency, right? So let's say I call this A here, and I look for another A. I definitely see another A, right? I see that A, then A there. But look at this. We have an A here, but here we have a B, right? That's not the same orbital, right? Those are completely different. And so we do not have the symmetry required to do this reaction. Okay. So this reaction will be symmetry forbidden, right? If I just did this with heat. So if I just heated this up, nothing would happen. Okay. So not every single reaction is symmetry allowed. It depends on if we have that symmetry, that orbital symmetry. And if it's there, then we can have this happen. Okay. Now, is there any way we can get this to work? And the answer is yes. We can get this to work if we do this. So actually, let me write this. So this will not work if I use heat, but if I use light, this will work. So why is it that light works? Well, it turns out that when you use light, For one of these, I'll just treat it in this one here. HV, right? If any of you are in physics, you guys know this, right? Electrons can absorb wavelengths of light, and they can excite electrons into their next orbital. Okay. I forgot the name of this. There's a name for this kind of series. I forget, but I'm not a physicist, right? So it's not totally my fault for not knowing. Anyways, if anybody would like to correct me, by all means, please do it. I would like to know. But now I can insert an electron into the system. Okay. And so now I can have an electron up here. And so suddenly my HOMO is no longer this electron orbital down here, right? It's actually going to be the orbitals up here. So this is now my HOMO. Okay. Actually, it's a SOMO because it's a singly filled. So we call this a SOMO, but that's whatever. Sorry. So if I think about this, right, this is my HOMO, right? The HOMO wants to interact with the LUMO. So now what I'm concerned with is the LUMO of the other molecule. So these electrons this electron wants to go and insert there. And now when I look to see for symmetry, these are exactly the same orbitals. So of course there's symmetry, right? Like I see that there is an A and I see that there is a B, right? And so the A and the B can interact with A and B here. There is orbital symmetry. This reaction will now work. Okay, so you can make cyclobutanes using HV. You can also do this back here too. You could have also excited the electrons if you wanted to. It doesn't really change anything, right? Maybe it changes who is HOMO and who is LUMO, but for the most part, not much craziness there. But you can totally add light if you wanted to. Okay, cool. So again, I know that the molecular orbital stuff is always the stuff that everyone hates every single year. Right? It's the thing that everyone's like, I wish I never had to learn it. But it is good to understand these ideas. I mean, it makes the reactions like this make more sense. And for those of you that are actually more interested in organic chemistry as you take it, it's this stuff this is the stuff that bridges sophomore organic to junior graduate level organic chemistry. It's understanding molecular orbital theory and how to apply it correctly. Okay, cool. All right. But like I said, right, or like we were talking about, right, Diels alder, cycloaddition, orbitally driven. Usually these reactions, they require super high heats, like 200 degrees Celsius. And that's just to do the normal form to form the cyclohexene. Not always the best thing to do. So we can do a couple things to increase the reactivity of these reactions. One of the things that we can do actually is we can take the diene and make it so that it always is in its reactive form. So if we look at the way that I've drawn the diene, right, I've drawn it in a way where the two alkenes are cis to each other, or what we call S-cis, right? They're on the same side. This is actually not the most favorable form because you can imagine cis isomers are always a bit unstable due to steric effects. In fact, most of these dienes want to be S-trans. Okay, so in order to increase reactivity towards Diels alder, right, we need to increase the probability that the diene is going to be in the S-cis form. And one of the ways to do that is to just stick it in a ring, right? So for example, let's say that I have this diene here. This is always S-cis. And so this is going to be one of the most reactive dienes out there because it's never going to have a time where it's S-trans. So you can imagine this molecule, this S-trans molecule, if it runs into a diene, no reaction is going to happen, right? Because it's not in that S-cis form. You have to wait for this to spin and then recollide with the alkene in order to get a Diels alder reaction. Well, this is never a problem if your molecule is always S-cis in a ring. This is always going to react. There's no doubt about it, right? So you can imagine any of these dienes where we're in a ring, right? Or at least stuck in a ring form, right? For example, this is not exactly in a ring, but it is stuck as a ring, right? It's forced to be a ring, and it's forced to be S-cis always. These are the most reactive dienes possible, okay? At least when we just consider the diene normally as a unit. Okay. Now I'll put here the normal diene here. So like a diene, that's just a diene, right? This is like sort of our standard. But the more that we add more steric things or things that can act sterically, the less reactive we become. So for example, let's say that I added in this methyl here. This is going to drastically reduce the rate of the reaction because now this really wants to be, away. So it really wants it so that we're away. So much so that if you actually put two of these guys in here, let's say you could put two of these guys in here. This is essentially NR. This is unreactive. If you see this is such a cheeky thing. Every year someone falls for it. If you see this diene, or you see this, you think this is the diene that's drawn on your paper, please don't draw a product. It is NR, right? That's the easiest NR problem on the planet once you recognize it. This spends 100% of its time looking like this. Almost never is it going to be in its other form. Okay, oops, sorry, like that. So always going to spend its time here. Another example of this is like, let's say you have an alkene, or say a diene where it's in a ring, but it's trans, right? In what world this is going to rotate to cis? Never. So this is never, ever, ever going to react. It's absolutely impossible for it to react. Okay. So just thinking about the reactivity of the dienophile, or sorry, the diene, one way that we can increase it is by putting it in a ring, right? Making it a ring is so much, it's so good. Okay. Another way we could increase the reactivity of a diene is, again, it's a nucleophile, so it needs to have electrons. So we can take a diene, and what we can add onto it is an electron donating group, or a group that will release its electrons into the diene system. So for example, oxygen atoms. So oxygen, right, will resonate its alone pair into the pi bond. And so generally speaking, right, because resonance is such a strong effect, it will donate electrons in, make this more nucleophilic. Okay, you can imagine that if oxygen can do this, nitrogen can do this just as well. Okay, now I'm drawing it on this position here, but it actually wouldn't have mattered if I put it here, right? That's totally possible as well. Just for the time being, right? I'm just drawing it in a way that's congruent. Okay. Now there is another type of electron donator. It's not as strong. So these are resonance donators here. Right. So I'll put here res. These are resonance donators. And we'll talk about this again with the directing effects for benzene, which, by the way, it's been about an hour. So I'm hoping that we wrap this Diels other stuff soon, and then we'll spend an hour on benzene and substituent effects. Cross my fingers, right, that we can uphold ourselves to that limit. Possibly not. But another type of group that does the same thing would be alkyl groups. So alkyl chains with absolutely no substituent on them, nothing that can affect their polarity. Right. These guys can donate via induction. So this is an inductive donator, but it's not as strong, but it's still able to release electrons into the diene, make it more nucleophilic. Okay. So on the other hand, if we want to make this less nucleophilic, less reactive, right, we need things that steal electrons. Usually the best thing for that are polarized pi bonds. So for example, carbonyls, absolutely the best at stealing electrons. This is an incredibly deactivated diene. A much more sigma or inductive related withdrawer is going to be a halogen. Halogens are inductively withdrawing. The larger the halogen is, the worse it is at donating. So, doesn't really do that best in activating the system, even though it has lone pairs. That will become really important when we talk about benzene reactions. So much so that there's some groups that are even, absolutely the worst. For example, like NO2 groups. NO2 groups are incredibly deactivating, as we'll see, because this is a cationic nitrogen, that nitrogen there. So I guess another variant of the inductive series is, let's say I have an alkyl group but with something electronegative on it, right? Like let's say there's an OH here. This is going to be very, very deactivated. This is like this carbon is not donating at all, right? For sure, this oxygen is going to be stealing electrons. Okay, so I think if I had to put it somewhere, I'd probably put it somewhere around here, right? If not equal to the halogen, but right there. Okay, cool. So in terms of reactivity, right, the nitrogen group is the most reactive, right? When it's conjugated, again, thinking about conjugation, right? Conjugation is what's leading to this electron releasing. R groups can donate inductively, which is not too bad. And then if anything takes away, right, then it's like, this is terrible. Absolutely the worst dienes possible. Okay. So we can take a diene and we can make it a better nucleophile, right? And you can imagine quite possibly the best dienes are the ones that incorporate the ring structure into, sorry, let me redraw this. So, no, that was fine. I'm just stupid. I just drew it wrong. So possibly the best dienes are the ones that have electron donating groups that are also in a ring. So absolutely the most reactive dienes look like something like this, or the better representation is something like a pyrrole, right? This guy here, which we won't talk about aromaticity, there's no time, but this is an aromatic molecule. So not only is it, aromatic, but it's also incredibly reactive. We call this, as you'll learn in 118C, this has a lot of pi juice. It's very pi excessive. So much pi juice in this guy, so it's very, very reactive. Okay, cool. Moving on to the dienophile, right? This is the opposite effect, right? So if you want to make it a better electrophile, we just got to add those groups that we just said were bad for the diene. So everything that we just said was bad for the diene is actually really good for the dienophile or for the alkene. So just go ahead and add those groups in here and just get, kind of power through this page. Okay, cool. So definitely don't want like these guys here. Okay. Now that's not to say that these guys can't do diels alder. It's just that when we're talking about traditional diels alder, we're talking about electrophilic dynophile and nucleophilic diene. By all means, you can do diels alder that are reversed. So we can do diels alders where we use something like this kind of dynophile and this kind of diene. This is actually a very common reaction. Some of you might remember this from the beginning of the quarter. I posed this question. This here actually would be a reverse. We call it a reverse demand diels alder, right? It makes your cyclohexene, although it makes it with these interesting like this with these interesting auctions in them. So totally possible, but not something required by the class. We are just going to think in terms of nucleophilic diene and electrophilic dynophile. Okay, cool. So that's what we can do with the diene. Now, the diene doesn't really have a ring requirement, but you can have ring dienes. That's not unheard of. Maleic anhydride is an example of this. Very powerful dienophile. Very, very powerful dienophile. Okay, so usually our best combinations are, again, ring dienes that have electron donating groups and some kind of dienophile that's incredibly electron deficient because it has like 2 electron withdrawing groups around it. Okay, cool. Now, before we get into stereochemistry, let's just kind of understand what reactivity does to the placement of groups. I understand that diels alder is always a very, very difficult thing to predict because there's so many things to think about. So let's kind of break it down. Let's first talk about regiochemistry, right? So reactivity wise, where do things want to go around the ring, right? And then we'll talk about, where things would be spatially, right? That's usually the harder part. So again, when we talk about regio, if I look at the normal diels alder, for the most part, you can kind of track where each carbon goes. For example, right, the diene is always going to be here, right? It's across from these 2 internal diene carbons that become the alkene. So a very good retrosynth tip if you see the cyclohexene in synthesis, or in a question if that's asking you for the 2 components of a diels alder, is to trace the alkene or use the alkene as your guidance, right? Cut those 2 carbons away to figure out what are your 2 components. And then these 2 carbons are here. Okay. So in a regular diels alder, this is what would happen, right? If I just add in, let's say, these 2 methyls here, right? Then it's really easy to track where these go. And again, we're not going to worry about stereochemistry just right now. We're just worried about placement, right? If I put, let's say, these 2 methyls here, right? Those go right there, right? So again, just tracing where those go, what things are going to go there. Let's say that I put a carbonyl here. Again, well, let's actually just do 2 just to keep things simple. That means that would be these 2 positions here. Okay. So in a case like this, where like the diene is symmetric or the dienophile is symmetric, it really won't matter where things go because it's symmetric. So you just kind of choose, right? It's totally up to you. Absolutely no stress, nothing to stress about there. Okay. Where things get a little more difficult though is when it's asymmetric, right? And we may have only 1 group. So this is what we like to call the regio diels alder. So for example, let's say that I have this oxygen group here, and then I'm reacting with, for example, this ketone dienophile. Okay, so both of these are asymmetric. So I mean, you can imagine that there's a couple different arrangements. For example, let's say that I draw in the diene part here. That would be this here, right? And then the ketone can either go right here or it could go right here. So those are the 2 dienophile carbons. It could be either one of those 2 carbons, right? Is it that both form, or is it that one is better than the other? Well, luckily for us, regio diels alder always usually has 1 answer, and that is going to be this here. Okay. I could also then pose this question this way, where I say, okay, let's say that the donating group is over here. So let's use an alkyl chain this time. Let's say the donating group is there, and then I'm reacting with a dienophile. Let me use a different one. Let's use NO2. Right? What's going to happen here, right? Again, we have the cyclohexane, right? The R group is going to be here. And again, either the NO2 is at this position or it's at this position here. And, we ask the same question, right? Is it going to be both or is one better? Well, it turns out that one is always better, okay? So why is it that I'm drawing out these products before going over the chemical intuition behind this? Because there's a little trick you can use that will always cut down this question to a 50-50 if you see it on the exam. What I want you guys to notice is the answer to the problem is always either the dienophile and the diene groups are as close as possible, or they are literally the farthest possible way apart from each other, okay? The terms that we like to use for this are para and ortho. Okay, this is more of a, benzene type thing, but it's okay if we use it here in this context, no big deal. But this is either para or ortho, okay? And it's basically a 50-50. If you recognize it's a regio diels alder because there's one thing on, usually there's one thing on the diene and usually one thing on the dienophile. If you recognize that there is some group influencing the charge density on the dienophile, right? You can boil it down to it's either going to be ortho or it's going to be para, right? It's either going to be close as possible or far as possible, okay? And that you basically narrowed down all your diels alders. But let's understand why that's the case, okay? So like I mentioned, on the diene, if you think about it, really the only thing that's changing is on the diene. But on the diene, we can either have a substituent on that top carbon or one of these side carbons. We call this a 1 sub. Call this a 2 sub. Okay. On the 1 sub, if I kind of trace where electrons go, what you'll notice is that we have electron density, right, flowing into this bottom carbon here, or the carbon that's directly opposite from the electron donating group, right? The oxygen sends electrons to this carbon here. So inherently, a 1 sub diene is always more nucleophilic on this bottom carbon here, okay? Now, I can also do this kind of same analysis with the 2 sub and notice that actually on the 2 sub, it's the carbon that's closest that we see this. So it's actually this next door carbon that it sends electrons into, right? And so inherently, right, this carbon here is more nucleophilic, okay? When I look at a diene, right, in any case, right, a diene will always have what we call an EWG, an electron withdrawing group. Pi bond is always going to be withdrawn into that pi bond, into that EWG. And so inherently, right, the carbon that's going to be positive is going to be this bottom one here, right, because this is going to be the, resonance form. Okay. With this becomes a game of charges, right? I want to line up my charges such that they match in the transition state of the Diels-Alder reaction. Okay, as you can see here, the minus and the positive line up just right on top of each other. So boom, boom, and then boom. Okay, and so what I get out is a product where the EWG, right, or like let's say like a ketone, for example. I'll use a ketone. That's always a safe choice. Okay. It's going to put this transition will put both of these as close as possible. So the methoxy and the ketone right next to each other. So that ortho that we were seeing. Okay. On the other hand, right, again, if I look at this positive here, right, minus and positive don't actually immediately line up. So I do have to do a little bit of flipping here. But when I do, you'll see, hopefully now you'll see what's going on here, right? But now I'll have the positive here, the minus here. These guys are lining up, right? All this lining up is going on. And what do you know? I get out this example, or I get out this answer where we have the EDG and the EWG, right? The methoxy and the ketone as far apart as possible, or the para product. Okay. So this is essentially what your Diels-Alders will boil down to. This is the game that you'll end up playing with all of them. It is a matter of where is the charge, where are the charges, right? Or who's producing the charges and where they lie against each other. Okay. Now, the way that you kind of take this problem the next level is you take the diene, for example, and you kind of give it 2 groups. So for example, you can give a methoxy here, and then possibly on this position, you give like an R group or something, like let's say an alkyl chain, something like that. So we have 2 groups that are, on a diene, and they have the potential to release electrons. Now, this oxygen here, right, donates electrons into the system, right? Again, it's going to donate opposite because it's a 1 sub. So this is going to be some delta minus, right? On the other hand, right, this guy here, Oh, sorry. I meant to put this up here. Yeah. Now this will make sense. Actually, you know, let's go ahead and just do that example that I just threw on there just because it doesn't hurt. You guys have probably already written it down. So, okay. So this will release electrons to that bottom carbon. Again, 2 subs will release to the closest carbon. So we actually get a doubling effect here. So sometimes you'll get cooperative groups where both groups will send to the same location electrons and actually just increase the rate like crazy. So these are usually the best examples. I call this the foolproof Diels alder because you could have messed up and looked at maybe you would have thought to look at this group here or one group or the other. You think one is right over the other and you kind of 50-50 which one to focus on. Doesn't matter because it's foolproof. Either when you look at it, you just look at this question right. Okay. And you can confirm that because you get that 2 sub, that you get that ortho sub, and then you get that para sub. So you get exactly what you want. This works perfectly. Okay. Where things are a little trickier though is when you have 2 opposing, right? For example, let's say I have again the R group here, and I have the oxygen here, because now you have the oxygen battling the methyl group because we have a minus sent here and a minus sent here. Question becomes, right, whose minus is stronger? General rule of thumb, resonance is stronger than induction. So if I have to choose who directs and who wins the perfect relationship, that's going to be the methoxy, the resonance donator. Okay. So yes, we do have a little bit of a cringe, you know, not ortho or para relationship between the methoxy and the ketone, but the methyl's not even a contender here, right? When we have the methoxy, who is going to be the one that directs this reaction. So this is usually the more difficult one where you got to think a little bit, but it's not too bad. Nothing too crazy, right? Don't stress too much, right? Sometimes you'll see a methyl being added in here. Again, don't stress too much. That's just going to go right down there. Has no bearing on the reaction because again, all we're concerned with is the EWG. Okay. Now, usually you will not see dueling EWG. So for example, you will not see like an NO2 battling it out with a ketone because when it comes to EWGs or dienophiles, both carbons are made sufficiently positive that either one could react. So it's not something that we usually stress ourselves out about. Usually you'll see a diene. If it doesn't have 2, it'll be on the same carbon. So for example, a very popular diene you'll see is this diene here. Sorry, dienophile that you'll see is this one here, where both of them are on the same carbon, or right, it's symmetric. So you only have to worry about which carbon reacts. Remember, when it's symmetric, your life is saved because it doesn't matter who goes where. Both carbons are getting the same thing. So usually when there's questions you ask, you'll get something like this. So it's like, oh, which carbon is the one that's going to react? And again, it's always that farther away carbon that's going to be the most electron deficient. Okay, cool. So this is the regio Diels alder. This is the Diels alder that gets asked 99% of the time, right? So really understand this. Understand the 1 sub and the 2 sub, how they can battle or how they can cooperate and how they're going to react with dienophiles, okay? And that's the regio part. So now we got the regio out of the way. Let's talk about the stereochemistry, which is usually this is the devilish part. Now, here's one thing that I always advise everyone because, it's always, the advice, it's always great advice. The regio part of a Diels alder question is always going to be like 80 to 90% of the points. So for example, if this is a 5-point question, 3 out of 5 of those points just go to get the correct regio. So if you can get the regio correct, you're getting probably 3 points out of that. The stereochem is what pushes you from the 3 to the 5. Okay. So if you on the exam are so lost, you're like, oh my God, I cannot for the life of me figure out what stereo to use or what product to draw, at least get the stereo down because you can get those partial credit points on that question, right? You get the correct, that's really the most important part is you understand the reactivity. Stereochemistry is important, but it's second to this, okay? Again, if you can get at least the correct relationship, right? At least the correct 1,4, the para or the ortho, right? You'll get the most partial credit you can get on that question. That's better than a 0. Again, always better than a 0. Okay. Stereochemistry is where you get the last 2, but stereochemistry can be a little difficult. So we'll look at each component differently, and then we'll add them together. So let's start with the diene stereochemistry. Okay. On the diene, probably the easiest group to side to resolve on the diene is these 2 positions here, these internal carbons, right? If you do a Diels alder, stereo is not a concern because look at that. They're just going to end up on the alkene carbon. So who really even cares, right? It just reacts and puts them there. So stereo is not a big deal. Where stereo does become a big deal, though, is when we start putting, components on these outside carbons, whether they are inside or they're outside. Okay. So when we're flayed out vertical like this, so either here or here, we call this an outside position. It's pointing outside. When it's on the inside here, when it's like flayed in like that, we call that an inside position. Okay. Inside positions are always going to be opposite to outside positions in stereochemistry. So for example, on this, we'll have a methyl here and we'll have a methyl here. But because this is outside, this is inside, right? These are essentially going to have a trans relationship. Now, do I know which one's going to be wedge and which one's going to be dash? No, I don't. Absolutely not. I do not know at all. But I do know that these two should be relatively different. Okay. So that's the most important thing. You guys can figure out relative differences, just not absolute differences. Like you cannot tell me for a fact that this is a wedge. You wouldn't have known that, right? But you can tell me that it could be either one of these isomers, right? Either one is possible. Okay, cool. Now you can imagine then that if these were both outside, right, then I would get, right, a syn relationship or a cis relationship, although this is equal to the supposed enantiomer where it's dashed, so it doesn't matter. But it is possible, right, to form this, right? So groups that are together on the inside or together on the outside are going to be the same stereochemistry, although actually on that note, right, inside groups, that's never going to react, right? This is unreactive. So this is going to be NR. So never have to worry about this. So if two groups are outside together, they'll be the same stereochemistry. If two groups are, one is outside, one is inside, they'll have a trans relationship. Okay. So that's how the diene stereochemistry works. Okay. Very, very simple. Dynophile, for the most part, is then the same, right? And that, especially if you have like, let's say we only have one group. I mean, if it's one group, then we don't really, I mean, it can be either wedge or dash. But if it's two groups, right, whether it's cis or trans, tells us whether they will be cis and trans in the end product. So this is meso, so it doesn't really matter. But let's say that I used a trans alkene here, right? Then these guys would be trans. Okay, and whether it is, I'll use plus minus here, but that just means that or I'll just put a racemic here, right? The other enantiomer, it's also a possible product here. Okay. So that's how the two components work in terms of stereochemistry, right? We don't know whether they are wedge or dash. We just know the relative differences, right? Like for example, this could have been dashes, although it's meso, so it doesn't matter. And same thing with this one, right? No one told me that the top had to be wedge. I just knew that if the top is wedge, the bottom has to be dash. So I can totally form the other isomer here as well. Okay, so we get that there. Okay, that's also possible. Okay, so the diene can have a cis-trans sort of relationship with its groups. The dienophile can also have cis-trans relationship within its groups. So when we put these together, so let's say that I have right this, and then I react it with this here. Again, let's focus on the diene part first. Look at my cyclohexene, right? Diene, I'm going to have methyls that are both that are both the same. So let's say they're both wedge. And then I have these ketones here that could also potentially be both wedges. So this is a possible product. This is possible, right? It's totally possible. On the other hand, right? So one thing is that everything, so if these are both cis, right? Then everything shares the same relationship, right? Or is the same stereochemistry. On the other hand, I could also even say that the possible product is, let's say this stays as a wedge here, right? What if I made these as dashes, right? And they're cis, right? So I have one where the ketone is the same, the ketones have the same stereochemistry as the diene methyl groups, and one where they're the opposite, okay? To kind of further exemplify this example, right? We can also have, let's say, trans relationships. And this is where things get a little bit of a nightmare here when you consider all the possibilities. But you could imagine that we could have potentially something like this, right? Where we have wedge on the top, dash on the bottom. But I mean, who said that these two wedges had to be next to each other? They could totally not be. And we could possibly have this as well, right? And we could have this here. We could also then consider, well, who in the world said that we needed to have the wedge on the top for the methyls, right? And you can kind of see where this is going, kind of goes on and on. But which one is correct, right? What do we go with? Do we draw everything possible, or do we just go with, the answer that looks the nicest? Or, do I just 50-50 it? Well, what I will say is on the exam, if you don't know, always 50-50 it. You never know, you might get partial. But there is something that does tell us absolutely every single time what the stereochemistry should be, what is the correct stereochemistry, and that is what I like to call the outside endo-pi rule. Okay. So this seems like a handful or a mouthful, but it's very helpful to say all this. Outside endo-pi. Okay, so what does this mean? What does outside endo-pi mean? So let's actually take this guy here, this particular example. It's easiest to see with the cis isomers first. Okay, so let's say I take this. Okay, so what outside endo-pi means is that the outside groups on a dynophile, okay, so the outside groups here of the dynophile are always going to be cis. So outside is cis to the pi groups on the dynophile. Okay, so the dienes outside groups are cis to the dynophile's pi groups. What's a pi group? Pi group just means it has a pi bond. So we can see here, these are pi groups on the dynophile because they have pi bonds that are conjugated to this dynophile. Okay, so if I were to draw, let's say, the actual transition state of a diels alder, it'll look something like this. Okay, endo just means that the ketone groups or the dynophile groups, these pi groups, will enter such that the ketone are inside the mouth of the diene, or they're endo to the diene, or they're inside the mouth of it. I guess a way to kind of to exemplify what the other way would be this would be exo, right, where they're not in the mouth of the diene. So you can see how these are facing the other side. They're like facing the same way as the mouth, whereas these are facing the same way. It's almost like these two are going in for like a little kiss or something, right? Why is it that this is preferred, right? Why is that we see this? The reason for this endo interaction is because if we kind of look at this here, this would be the normal diene interactions. The pi bonds, those pi group pi bonds, actually have the ability to interact with the dienes. So there's these interactions here. They can interact with the dienes pi bond. So if the orange is the main interaction, right, the main diels alder interaction, so the what we call the primary diene, primary DA interaction, right? The blue dots are what we call a secondary pi interaction. And this secondary pi interaction serves to stabilize the intermediate. So when these ketones enter into the mouth of the diene, right, we get this extra stability, this extra interaction, right? We have a kinetic preference, right? So remember that idea that kinetic product always forms first. So we form the kinetic product, and that's the fastest. That's going to be the endo product. And as a result, right, again, the outside groups are always going to be cis to any of our pi groups. So these wedges, right, or these methyls, if I choose to make them wedges, then the ketones will also be wedges because they are the pi group. So this is actually the kinetic product or the major product of our reaction. In this class, we will always be following endo rule, meaning that we will always want to form the endo product. We always want to draw the endo product as the answer. Okay. On the other hand, right, the other product that would form is what we call the exo product. That product is a bit more stable, generally speaking, but it's not something that we'll concern ourselves with. We always want to draw the endo product, okay? So we always want our outside groups to be cis to the pi groups on the dynophile, okay? So for example, let's say that I have this here, and I do this same reaction. Again, if I choose to make the top one a wedge, the bottom one a dash, right? Top is our wedge, is our outside group. Bottom is our dash, or inside group. We want our ketones to be cis to that methyl. Okay, and this is our correct answer, as opposed to having the cis as dashes. Okay, cool. All right. So we can take this and we can apply this to pretty much any diels alder we do. For example, let's say that I even go and I do this here. So I choose to use this methoxy here, and I choose to use this this dienophile here, right? I can go ahead and draw my cyclohexene. Again, I get most of the partial anyways if I just draw the correct regiochemistry. So I get this. So this is a 1 sub. This is a dienophile, right? So I get this. I already get most of the points just drawing that correct product. But when I think about stereochemistry, again, if I choose to make this a wedge, right? If I say that this methyl is a wedge, then I know that it's an outside group. It should be cis to the pi group of that dienophile. So this will also be a wedge. Now, keep in mind, this will be racemic because we don't know if they're wedges or dashes. We just know the relative stereochemistry, nothing about absolute. Okay. Now, trans dienophiles are a bit more difficult to think about, at least, when we think about the endo transition state, because considering that one group is always different from the other, if I kind of draw the transition state again, well, one ketone is always forced to be, it's always forced to be not endo, right? Only one ketone can be endo at a time. So in these instances, it's totally, it's easy to freak out, but it's okay. Don't stress too much, right? I would just, right, again, let's say I make these wedges, right? Just choose one of these to be your endo group, right? Let's say in one reaction, this top one's the endo group, like that goes endo first. Then this will be a wedge, right? This will be a dash. And then again, no one ever said the top one had to be the only one that does this, right? That goes endo, right? The bottom one can also go endo. Or I guess another way of thinking about it is that we're just reversing that trans stereochemistry. So we can have it such that the top one goes endo first, or possibly the bottom one goes endo. Okay. Cool. All right. So quite, usually the most difficult questions of these are the ones that involve rings. So we haven't really done a ring example, so let's go ahead and just do one. Let's say that I have this here, this ring example here, and I'm reacting it with, let's say this dienophile here, right? What should I expect to be the product of this reaction? So rings, don't be afraid of rings. All they really do is add bridges. So in the diene, if I do this as a reaction, right, all it does is it adds a bridge. So remember, diels, alder, the diene and the alkene give you the cyclohexene. This component here is just a bridge. So I'll get a nitrogen, right, carbon bridge just like that, with that methyl sticking out of that nitrogen. I'll put it up this way, I guess. Okay. Now there are these hydrogens here that I like to highlight because they help me realize, oh, these hydrogens are outside, so the bridge must be inside. So when I consider that this is an inside group, let's say that I make the bridge a wedge, right, because it's pointing up, right, then the dienophile group should be opposite to the bridge, right, because this is an inside group and I want my outside groups to be the same as the dienophile group. Now, if I look at this here, I have a methyl and I have a ketone. Remember, it's the pi group, right? It's the pi group that has to go endo. So I want my ketone here to be dashed because that's endo, and my methyl here will be wedge. Okay. Hard to see here, but I am still retaining the closest possible relationship between the EDG and the ketone. It is a little hard to see here, but these are right next to each other. Usually, though, the nitrogen's up here. That's why it's easier to see. Okay. You can also sometimes see this represented like this, like on a key or on some practice. Don't worry, this is not meant to confuse you. It's just meant to be the 3D representation to kind of show you what it would look like. This is actually where the endo term came from. Endo came from the fact that if you were to do these diels-alder reactions, yeah, so let me see in here. If you're to do these diels-alder reactions, right, the endo comes from the fact that, hey, the bridge and the dienophile pi groups were always opposite to each other. They were always pointing down. So that's where endo came from, actually, was this observation here, okay? So if I want to draw this normally, that would just be an oxygen bridge just like that. And I would have, again, these CNs that are opposite, right? And I have these methyls here. Okay, cool. All right. I think that should be good on that. The last thing I'll go over for diels-alder, because again, we're kind of cutting into time here. I mean, we went way over time actually, and we still have to do benzene, which makes me a little worried this is going to be a little long. I think we'll probably take another hour and a half, which kind of sucks, but whatever. The last thing I'll leave this on is how to predict the products or predict the components of a diels-alder. Very, very simple. Remember, a diels-alder itself, if I have the cyclohexene, this gives me all the power in the world, right? Opposite to the alkene is the diene carbons, So I can always get back to here, where these blue carbons are my diene carbons. And then these carbons, sorry, dienophile carbons, and then these green carbons make up my diene here. And then obviously these orange carbons are then these guys here. So no matter what you're given, you can always get back to some reasonable product, even if it's something as crazy as this, right? Let's say you're given something like this and you're told, hey, you know, give me the two components here. Now, if your exam writer really hates you guys, they'll do something like this, where they put the alkene up here. And then let's say they do, what else could they do that could make your life really hard? They could do this, and they could do this and this, right? In an event like this one, where you have like this 3D structure and don't know where to go, again, use the alkene to guide you. I see an alkene here, so I know that this part here is going to be part of my diene, right? This here will be my dienophile. Sorry, this is my here, my diene, right? Those are my, oh, sorry, I used the wrong, that's why I messed up, I used the wrong color. So this part here will be my diene. I'm also willing to bet that because, hey, we have an oxygen group that can release electrons into that diene to make it more reactive. The question now becomes is, which two carbons are my dienophile and which two carbons are just part of the, the diene as a ring? And so remember, dienophiles, we want groups that are electron withdrawing or, willing to steal electrons. And so you can see here, we have CNs. Those are definitely electron withdrawing groups compared to, let's say, like if I had these two methyls here. So I want to cut here. And what I get, right, I can, we can kind of draw it like this. But we'll get these two components here. Dienophile is not very easy to see. Diene is going to be a little bit hard, but you'll have to draw these pi bonds here and then kind of draw everything in. Well, I had something like this. You'll probably want to number your carbons, but, you'll get a diene where it's kind of bound to two. I mean, actually, what you can do is this, right? 1, 2, 3, 4, 5, 6. So it's a 6-membered ring, this diene here. And you can draw the diene in. On one end of the diene, there's going to be this here. And on the opposite ends, right, on those ends that don't have the diene carbons, we're going to have those two methyls. Obviously, I chose the hardest example possible to ask this question because I wanted you guys, again, to just see if it was the hardest possible variant, how we could do this. On an easier example that's, usually has, right, like a bit more planar and easier to see, right? We can just look from here. Okay, look at that. We see our diene carbons, right? These here. And so our dienophile carbons must be these guys here. So we cut like that. And then we get our two components, right? We get this, which we turn to a diene. And then we get this, which we turn into our dienophile. Okay, cool. Very popular question, which is why I'm bringing that up. And with that, I'm going to unfortunately have to call it on the diels alder. Again, I know I'm going through this pretty quickly, but most of these things, I mean, when we look at the problems, you'll see how these concepts play in. And also there's still the ATC, right? And there's other resources you can use to get an even more in-depth practice or in-depth talk about these things here. Okay. One thing you'll notice is that the mechanisms in this section are not very crazy. I mean, at least in diels alder, there's just 3 lines. So you won't really see mechanisms in chapter 14. All the mechanisms will be chapter 15, 16, where we're talking about benzene electrophile formations and directing effects. Okay, cool. Now, with that being said, unfortunately, because it is now been, I guess, an hour and a half, we do not have time to go over aromaticity. That's okay. There is the aromaticity guide that I sent out. I might have a video where I talk about it. So I'll see if I find it, I'll send it out. Yeah, I think I will do that. I believe I do have a video on that. So I will just send that out alongside that just to save time. But we're going to talk about benzene reactions here. The number one thing to know about benzene reactions is that there's kind of 2 categories to this. There are what I call the dehydrations. And there are what I call the Lewis acids. Okay, so dehydration, as the name would suggest, just means we're losing water. And the main giveaway that we're doing that is when we're doing a reaction in H2SO4. So whether we're doing SO3, H2SO4, or we're doing HNO3, H2SO4. Okay. These mechanisms are super simple. Okay. You are just taking the top component, or you're taking the component in the solution, and you're taking water out of it. For example, if I'm doing HNO3, right, all I'm doing is I'm making water, right? Because I'm dehydrating. So I just make water out of this OH here, right? I lose it. And guess what? I form my NO2 cation that my benzene wants to attack. Okay, so super simple, right? This takes less than a second. And for the most part, I know a lot of you guys are worried about reversibility arrows. You can kind of, most of these reactions are for the most part pretty much always reversible, the dehydrations. So, I mean, if you want to be nitpicky about it, you can look at which ones were and which ones aren't. But for the most part, this is the case. Okay. But anyways, I made water with OH. I lost it. I made the cation. And with every single benzene reaction, right, we get an attack on the benzene, or sorry, on the nitrosyl, on this NO2 cation, right? We get a resonance of electrons around the ring, right? But eventually something just takes off this proton, right? And we restore aromaticity. Okay, that is every single benzene reaction, by the way. Is benzene attacks an electrophile. Electrons run around in a circle, trying to avoid instability, and then something deprotonates that position. You add the electrophile to restore aromaticity. Okay, super simple, not too crazy. Guess what? Same thing with H2SO4. So H2SO4 again. How can I make water? Right, not too crazy. Make water like that, and then we go ahead and we lose it, and what we get out is the SO3H plus cation. Which, hey, guess what? If I just replace this with this, it's the exact same thing. Okay, so dehydrations, super simple. Just lose water. These are not too hard to remember. Okay, so I'm gonna, just for the sake of it, just to get me space, I'm gonna get rid of these. What these guys add to the ring are SO3H and HNO2, or sorry, NO2. On any position, by the way, on a naked benzene, as I refer to it, any position. The Lewis acids are also fairly simple. There are technically 3 types of this, but you usually have some kind of Lewis acid, whether it is FeX3 or Al, some kind of metal. So I'll just put here Me to stand for metal, right? Some metal, right? MEX3, and then some kind of halide system. So, for example, let's say that I have this here. Probably the one we'll talk about the longest on here is just the Friedel-Crafts because of all the exceptions and all that stuff. But outside of that, we won't really get too much into it because we do have to get the substituent effects and then the actual exam. But for the most part, we'll get this. Right. For this example, we'll get this. But if we have, let's just do the example here where it's R here. Usually you'll get some kind of rearrangement. That's the thing that kind of sucks with these. Little tip here: Friedel-Crafts alkylation makes branch centers. Yeah, we'll talk about alkylation the most. We want to talk about the others. It's just very simple, these other ones. But we'll talk about alkylation and acylation. But this here, we can do a reduction and we can get a linear center. So this is actually the solution to a problem that we will see coming up. Okay. For these Lewis acid reactions, it's usually very simple. Usually X just attacks the metal, right, to form an adduct. And for a majority of these, this is so for at least for halogenation, this is the active electrophile. So this is actually what benzene attacks. For alkylation and acylation, there's some extra stuff that goes on, but nothing to worry about there. We will just go over it now. So again, I'm not too concerned with the dehydration stuff. That's pretty simple, straightforward, and I'm not concerned about halogenation. It's very, very straightforward. The only thing I'll add here is that you can actually reverse this reaction here. So all the arrows in sulfonation are reversible because we can reverse this with H plus H2O. Sorry, H2SO4, I should say, actually. Okay, cool. So let's talk about acylations and try to hurry this up. Cool. So alkylations as a reaction is really interesting. If I take, let's say, an ethyl chloride and I react it with a Lewis acid, right? Again, the metal is so strongly electron deficient that even a halogen is willing to donate to it. It entice a halogen to do something it normally never does. And so what we end up getting is this species here. And so for like an ethyl chloride, this is the active electrophile. If X tries to leave here, you'll notice that it'll form a primary cation. So it's never going to do that. That's just not possible to form. Maybe let's consider, maybe if I have the allyl system, this will happen, right? Because remember, we're all talking about the allyl. So keep that in the back of your heads that we can do that with the allyl. But with a normal alkyl, right, an ethyl, for example, it's not going to happen. Again, benzene will do the thing that benzene does, which is it goes ahead and attacks the carbon there. Right, we'll get the ethyl on this carbon. We'll get a cation. Be sure on the exam to write all the resonance forms that are possible. Those are always graded. I already passed the class though, so I can skip those because clearly I understand them, right? I get away with that. But what I have left now is this here. So when it comes to methyl and ethyl, right, because you can't form a cation, you usually just get a straight up addition of the chain straight onto the benzene. Although there is one problem here, as we'll talk about hopefully within the next 10 minutes. Whenever you have these alkyl chains, again, remember alkyl chains are inductively donating. So inductively donating means more electrons. Benzene's acting as the nucleophile in these reactions. We're making the benzene more nucleophilic. And so usually what you'll actually get is actually a polyalkylation. Okay. Now, don't worry about polyalkylation too much. This is just a problem to know, right? So this is problem number 1. So I'll call this P number 1, first problem that we'll see. Okay. Now, if I advance this into the propyl, you might consider, okay, maybe the same thing happens. So we get the ALX3, we get the minus, the plus, and then the benzene should just attack it. Well, turns out that's not actually what happens. What ends up happening is this position here with the hydrogen that's secondary can actually kick off the X group. We have a a spontaneous rearrangement or a concerted rearrangement to form a carbocation. So Friedel-Crafts alkylations are formally SN1 type. Sorry, SN1 type. Oh man, you can tell I've been talking too long. My throat is so dry now. They are formally SN1 type reactions, and when they can form stable carbocations, they will. Okay. And so linear chains that branch longer than 2 carbons are usually plagued with these rearrangement issues. I'm going to go ahead and skip in the future a little bit here, but we're going to form this branch center here. So Friedel-Crafts is a reaction, not very good for forming the linear center, but it is very good at forming branch centers that can, accommodate carbocations really well. So we never see this here. Okay. So anytime you see a product or like an alkyl bromide or chloride where clearly there, you can get a rearrangement to a better carbocation, by all means, that is going to happen, right? So the active reagent is actually going to be this here. So a way to kind of draw this easily is you can replace the bromine with the cation, and then you want to switch H in the cation. So H would go here and the cation would go here. So you can draw in the H if you want to, you don't have to, but that's going to be what the benzene attacks. And so this alkylation product, I'll put this here, AlBr3, right? This is going to go ahead and kick that off. What we're going to get instead is actually going to be this here. Okay. So branching centers, very, 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 very easy to make with alkylations, and it's usually the problem. Okay. In fact, actually, just to even avoid this, or even like to avoid the surprise, is just start with a branch center, right? Just start with something like a tertiary bromide, and then just do this reaction, right? AlCl or AlBr3, right? I have nothing against iron. I'm just trying to get through this really fast, and it's the first thing that's coming to my mind. Okay, because what you'll form with this is then the cation here, and that will attack it here. So again, Friedel-Crafts alkylations are formally these are SN1 type reactions. So thinking about the cation that can form, right? And so that's why I mentioned that thing earlier, is that, hey, imagine if your cation is alo, right? Then this will form an alo cation very well with, let's use Fe this time. Ferrous bromide. This will form a cation very well that benzene can attack. Which again, I'm just apologize for being very lazy right now. I just have to kind of speed up in time. Okay. And so you can imagine you can do some pretty cool stuff here, right? You can add this to a benzene. Now you have alkenes that you can do alkene reactions with. We have an allyl position we could do some crazy stuff with, like maybe, we didn't really talk about this, but if I make the allyl anion here, maybe I add like an epoxide, and then, oh, look at that. What if I did this? What if I brominated, right? That alkene, right? Ooh, look at that. That looks like a great reaction that I could do. Wait, 1, 2, 3, 4, 5, 6. Yeah, actually, probably the 5 will form faster. Yeah. So we could do something crazy like that, right? It's totally possible. So cool things to think about, right? And maybe possibly a reaction that I might have written. But yeah, cool. So alkylations are always going to overreact, right? That's kind of a thing to just to know. And also that they're just going to rearrange. So there's really no way to form these linear centers. They're always just going to rearrange. Okay. Now, one last thing to talk about is that you can also have intramolecular type fatal crafts. So for example, you can have something like this, AlCl3, right? And I apologize that I'm having to rush here, just trying to get through this review very quickly, right? We can go ahead and attack right there, right? 1, 2, 3, 4, 5, which means that we're going to form a 5-membered ring as such. 1, 2, 3, 4, and 5. 1 and 5 are the benzene ring. That makes us 4, 3, and 2. On 2, we have these 2 methyls, so we're going to go ahead and draw them like that. Okay, so intermolecularity, totally possible. I think one of the craziest one I've seen is when it's like they give you like a chain like this, and then you react this with the benzene. That's probably the craziest one that I've seen. And I mean, you can see where this kind of goes, right? It's kind of like pincers grabbing onto the benzene, right? So to make something like this. Okay, cool. So again, rearrangements for linear centers. So if you have linear bromides or chlorides that are longer than 3 carbons, so for example, this, right, this, it really doesn't matter. As long as it's linear, it's going to rearrange. If it's already tertiary, secondary, the cation will just form because, again, it is an SO1 type reaction. It's going to take place. To even further exemplify this, a very non-classical way then to do these reactions is taking an alkene is reacting it with something that's non-nucleophilic acid. So, for example, HF. HF will form the cation on this alkene. And guess what? Benzene, it's not like benzene knows what was made by fatal crafts and what wasn't. It is still going to attack this thing here. Okay, so we have the ability to add a lot of things, right? If we just think about it. Very common, not trick, but, you know, something that catches people off guard. Very common reaction, that one. Yeah, cool. So what's the solution to this? What do we do to solve this? We use acylation. So acylation involves the acyl chloride. Okay, so this can be really any kind of linear chain, doesn't really matter. But the way acylation works, well, actually, initially, oxygen bonds to the aluminum. And the reason for this is because for reasons that aren't really worth getting into. But oxygen just makes really good bonds with metals. And so initially, what you'll see is the addition onto the oxygen. But very slowly, this will go onto the chlorine. If you want to impress your TA, you can say hard soft interactions, and they'll be like, "Wow, who taught you that?" And you can be like, "Oh, you know, I already knew that. I'm just smart like that. You know, totally, you know, trick your TA into thinking that you knew this stuff." But anyways, the chlorine will eventually add on there, and always what we see is the chlorine leaving. Okay, so why is that we always see that? It's because when it does leave, what we form is this cation here, which doesn't appear to be at first, but it's actually resonance stabilized. So sorry, let me draw this better, just so you guys can really see that. This cation here is resonance stabilized. Okay, this is known as the acylium cation. Okay, and it is a triple bond to oxygen. But this here is our solution to our rearrangement problem because we have a resonating cation. So the cation is actually stored in the oxygen, and oxygen, for as far as we know, doesn't really do rearrangements, right? Cation rearrangements at least. So benzene will always choose to attack this carbon here. So it's always going to be on that carbon that holds the rest of the group, right? Which leaves us with this here, right? Again, there'll be a cation here. Something will go ahead and do that, blah, blah, blah. Usually with these metal reactions, it's usually like the bond between chlorine and a metal, or the halogen and the metal that does it. I know I haven't, again, I apologize, I'm rushing. But there you have it, right? We have our acylated product. Now, the one thing you need to know is, again, remember, oxygen makes really good bonds to metals. So initially, we'll get a bond to the metal just such. But if you do an H+ workup, which you'll see with every single one of these, right, you'll get rid of it. So don't forget that H+ workup. Otherwise, your TAs will massacre your points. That's how we get to that. So acylation, right, on one hand, it prevents this rearrangement issue that we were having. How can I get this to the linear form? You can do what we call a Clemmensen reduction, which is zinc HgHCl. Right, gets us down to this molecule here. Okay, so we get that linear center now that we were unable to access before. So this is our access to linear centers. Another thing that this helps us with is that overreaction problem that I talked about. So again, usually overreaction is usually a vocab term that's tested. It's not very something that you have to worry about in predictive products or synthesis, but because the carbonyl group is withdrawing, it takes electrons away from the benzene, like we talked about with the dienophile. It actually reduces nucleophilicity, so it prevents the reaction from moving forward. Okay. Now, one last thing to understand about both alkylation and acylation, these guys actually suffer from one thing. And it'll make sense when we get to the next section. But if we have something that we call a meta director, and we try to do either Friedel-Crafts reaction, so it doesn't matter which one, A can stand for anything here, it does not work. Okay. And that's just because the carbocation is just not a very strong enough electrophile, not as strong as the sulfur electrophile, the bromine electrophile, the nitrogen electrophile. Okay. Cool. So that's our Friedel-Crafts reactions. And again, we can do intramoleculars. That's totally possible. In fact, we can almost even build one. So I'll just very quickly walk through a possible synthesis you could do. I was almost considering drawing this or making this one of the problems. I don't know why I didn't. I think because I wanted to be on the other one. Oh, actually, now I think about it. So I forgot. I don't remember if she teaches you this actually. You can do Friedel-Crafts with carboxylic acids. I don't remember if she teaches you this actually. I guess maybe not. You cannot do this. 1, 2, 3, 4, 5. So you can also do with the carboxylic acid. That'll also work. I don't think she taught you guys that. So womp womp. I should have. Oh, but you know what? One thing you could do if you want to really impress, I mean, I guess it'll never be asked, but you guys might remember a way to turn OHs into CLs. So you could make an acyl chloride. You could probably guess just from last quarter. Either you think HCl or you think SOCl2, and the answer is SOCl2. So you could have done that, but whatever. But yeah, you can use carboxylic acids too. That'll also work. AlCl3 will pull it off. Okay, cool. Oh, which actually reminds me then that there's one last type of molecule that you can use. It's the anhydride. Don't let the anhydride scare you. I know there's so much stuff going on. It's exactly the same thing. So first we get a complex on the carbonyl. Then we get a complex on the other atom. So in this case, the oxygen down here. And then remember, this will just break a bond. So kind of focus on one side, I would say. And then you form your acylium ion. Okay, so don't let this stress you out. Sometimes you'll get the cyclic version too. Same idea, right? I'll just kind of speed up in time here, right? This is plus, this is minus. So this will go ahead and break from there. And so we'll get this here. Okay, and that's your acylium ion. Now I will go ahead and draw the product of this after the benzene has attacked it. And I'll kind of draw in a way that mirrors the way that this looks so that you can kind of see where things are going. Okay, it'll look something like that. Okay, cool. All right, again, sake of time, shoot, I think it's been 2 hours now, so definitely did not abide by my own rules on this. That's okay. It's what we got to do, right? Get the high yield information. So we're going to just call it on this. Just do your practice. I actually do have a worksheet I can send in, just extra practice problems. I'll do that. But anyways, with that being said, now we can talk about directing effects and strategies. So benzene, again, when we have just benzene and we just do an attack on it by an electrophile, right? It goes anywhere because hydrogen does not direct, right? But the electron we add could potentially have some directing effect. For example, one effect it can have is that it gives electrons into the ring. And so if we kind of draw the resonance forms that are possible, right, we get this, we could potentially get this here, right? We also get ones where the anion's on the left side, but it's exactly the same as this one, so I won't draw it for sake of time. But as you can see, we have groups that potentially donate electrons into the ring, right? Making the benzene, well, more nucleophilic. So we have, we call these EDGs, right? Give electron to ring, right? Makes it more nucleophilic, right? Which makes it more reactive. Okay. And if we look at where the electron density is, it's on these positions that are right next to and opposite to the ring. So if I call this ortho, meta, and para relative to E, right? We have electron density ortho and para to the ring. Okay, that's where the electron density is. So if I were to add an electrophile, where do you guys guess that's going to go, right? Adding an electrophile E plus that wants those electrons, right? Our EDG is going to add electrophiles ortho and para, okay? Usually about 60-40 in favor of para. You can imagine because of sterics. Both have the same electronic effect, right? But para is less sterically hindered. So usually about 60-40. For majority of reactions, you're just always going to assume that it goes, for both. Just a couple reactions where they won't, and we'll talk about those, right? But again, we're going to be giving electrons into the ring, so it's more nucleophilic, more reactive. And then, right, the electrophile, right, it's going to add ortho and para positions because that's where the electrons are. Okay, so we call these ortho-para directors. Now, these guys are, for the most part, really easy to identify because I gave away one thing, right? They usually have a lone pair. So when we think about that, we think of like oxygen atoms directly connected. We think about nitrogen atoms that are directly connected with those lone pairs. Those lone pairs are where they're going to drive this reaction. Now, alkyl groups can also participate, but they are only inductively withdrawing. So when we think about in terms of reactivity, these are the weakest ones, but they still have an ability to do something, right? So we will give this an arrow, right? These guys are inductive EDG, right? And these oxygen and nitrogen atoms are resonance EDG. Okay. Now, one really weird thing here is that oxygen and nitrogen are also deactivating in a sense, right? Because they are also withdrawing. So these guys are inductively withdrawing, right? So they withdraw electrons. Now, the resonance effect is a bit stronger than the induction, which is why they are overall donating and overall activate. There's another term for this. We call these guys activators, right? And also the reason why these guys tend to, increase the reactivity of a ring. Okay, so every heteroatom you see will have some degree of withdrawal, but in the case of oxygen and nitrogen, where their donating effect is just so strong, it just takes over. Okay, cool. It also explains why the ortho position is also a little bit disfavored, right? Electronically, if we have an oxygen here, for example, it's going to withdraw most powerfully from the ortho position compared to the para. So that's why we get this sort of 60-40 split. Okay, cool. So these are our main groups. And again, anything can be here, here, here. It doesn't really matter. The point is that the atoms' electrons are what are next to the ring. Okay, so what we'll do the opposite thing. Is there anything that I can add that will do the opposite? And yes, there is, right? I can add an electrophile. Usually this electrophile has a cationic charge, or it has like a pi bond to something electronegative, right? And this thing, right, is going to be a very good withdrawing group, taking electrons away from the ring. Okay, so I'm unfortunately not going to go through writing everything out again, just because, again, in terms of time, things are not looking very good right now. Probably going to have to speed run this exam. You'll see how fast I used to take it back when I was taking these exams. Oh, sorry. I do want to draw this. Okay, cool. But we have now what we call a meta director. So again, if we look back here, right, this is going to be what we call an EWG, right? Takes electrons from ring, right? Which makes it less reactive, right? Less nucleophilic. Okay. So generally speaking, these rings are what we call deactivated. Okay. And we think about where the electrons are. Well, they're definitely not in the ortho-para positions because those positions are positive. They're cationically charged. So all that's left now, right, OMP, is the meta positions. The electrons are at the meta positions. So in fact, when we do our reactions with these guys, right, with our EWGs, right, we will only get meta product. Okay. So electrophile will go meta position. Okay. Did I miss anything else? No. Pretty much it. So there's a lot of these guys. Most of these should be recognizable. NO2, right? CN. Now kind of, I'll draw out what these guys look like so you can see why it is that these guys have such a powerful effect. Okay. Ketones, aldehydes, SO3H, And hopefully you guys are seeing the pattern here, right? I mean, there's a cationic nitrogen, cationic carbon, or these carbons that are pi bonded to these electronegative atoms, sulfur pi bonded to all these electronegative atoms. And then we have NR3 plus, right? Very, very important here. NR3 plus, right? It has no lone pair. So it's not like N with a lone pair. And then CF3, okay? For the most part, these guys appear in red. Actually, let me make sure. I do want to make this distinction here. Right. These guys here in purple are only inductively withdrawing, although they're very powerfully inductively withdrawing. These guys up here are inductively withdrawing, but they're also resonance withdrawing. So they are very, very powerful. In your notes, actually, is a hierarchy you might want to know for which ones are stronger than others. But generally speaking, you know, these are the guys here. Okay. So these guys are deactivators. They have a low reaction rate. Okay. Cool. So if you see these guys and we're adding electrophile, we know that things are going to go meta. Okay. So best way to test that you understand everything I just said is we do what I like to call the Davis benzene problem. And the reason why I call it that is because this here looks like a benzene ring, or it looks like a bike kind of, or I guess it looks like a guy that's like running very fast, right? You know, it's running to class with huge benzene legs. But anyways, if I were to add an electrophile, which ring would it go onto and what positions? So you can take a second and think about this. But all it takes is think about what effect does that atom have on the ring. So I have a carbonyl, I have an oxygen. What effect do they have on the adjacent rings? This carbonyl is electron withdrawing because it's a cationic carbon bound to the ring. This is an oxygen lone pair conjugated to this ring. So this ring has higher nucleophilicity. This one has lower. So the electrophile is always going on the oxygen ring. Now, where is it going? Probably going to go orthopara, right? Because that's where electron donating groups tend to direct. And again, for a majority of groups, you can assume for the mono subs that it will go for both, unless it is particular groups that are very, very bulky. And we'll go over those in a second, what groups those are that are very particularly bulky that they would not want things ortho to them. Or maybe electrophiles that are bulky that don't want to go ortho. Cool. All right. So that's the Davis benzene problem. Hope you guys enjoyed that. Cool. So again, I mean, some of these things you guys know how to add onto a ring, which is pretty cool. Like, for example, you guys know how to add on NO2. That's HNO3, H2SO4. Right? Imagine that I wanted to add on another electrophile afterwards. So let's say FeBr3. Br2, right? Again, think about what the NO2 does to the ring. That makes it electron withdrawn. It makes it so that the meta positions are the most likely positions to be attacked. And so that's where that bromine's going to go. Yeah. That in mind, actually, I did forget to talk about the halides. Halides are a bit of a what's the term? They're a bit of an enigma in that they have lone pairs. So let's say I have a halide. They have lone pairs. Okay. So they should have qualities in which they donate electrons into the ring and, you know, activate the ring, but they also have they also have induction. And so they can also withdraw from the ring. So what do we have to know about the halogens? For the most part, the halogens are capable of donating to the ring sometimes. So these guys are orthopara directing because they can donate their electrons in, but it turns out that their induction actually is stronger. So overall, these guys are deactivators. So a lot of the time people teach this as halides are these exceptions that they're supposed to be meta directors, but they're actually orthopara directors. But I don't like that. I like to think about them rather as the exception for the orthoparas, because when you have the lone pair, right, that's a very clear indicator of orthopara direction. It's just that it just so happens that their induction is stronger. So I like to think of these guys as orthopara directors that are deactivating rather than deactivators that are orthopara, if that makes sense. Okay, but these guys are deactivators, so they would land into here. They would reduce the rate of a reaction. But it makes sense that they would go orthopara, right? It would make sense that they would direct orthopara. Okay. Usually I have a whole spiel with numbers, but time is of the essence today. So I'm hoping to finish within 30 minutes, maybe. Not even. Yeah, this is gonna be a long one. I apologize. It's already 2 hours, so maybe 30 more minutes. Cross my fingers. But let's say that I do FeBr3, Br2 here. so that I get the bromine at this position. And then, right, I add in HNO3, H2SO4, okay? Right, this is actually gonna make it so that the bromine now adds the NO2, both ortho and para, okay? And so again, unless told otherwise, which we'll go over in a second, right, we can assume we're gonna form both. So look at how the order of addition changes drastically what we get. Whatever you add into the ring first is going to dictate what you get, okay? Now, keep in mind that one little fact that I told you guys, right? Let's say that I wanted to do a Fredel Crafts on a ring, but I have something like HNO3 on that ring, right? Or NO2 on that ring. Remember, Fredel Crafts, any kind of Fredel Crafts, alkylation, acylation is just not going to work, okay? So how do I, so let's say that I, H3O plus, right? So let's say that I somehow wanted this ring, right? How could I do it? How could I get this? How could I get this here? Very, very simple. All you have to do is reverse the order, because there's the only limitation is that you cannot add Fredel Crafts for electrophile to a meta directing ring, but the Fredel Crafts electrophile itself is meta directing. So you can still do the reaction. Remember, don't forget the H plus workup, and then add in the HNO3, H2SO4. And get the ring that you want, you know, just have to go the other way. So one little, just wanted to make sure I said that out loud, because that's something you do need to know, could help you out in the synthesis. Okay, cool. So now that we know what to do when we have one group on the ring, right, and looking at the substituent effect of one group, the question then becomes, actually, wait, before we do that, let's talk about the steric stuff. So one last thing to know is what are the groups that are steric? So for example, the groups that if I add them on, they're going to direct opposite, or they're always going to direct para. One of those is tert-butyl. So let's say I add in tert-butyl chloride. Major product of this is always going to be the para product, because as an electrophile, this is incredibly sterically hindering this guy here. So it's very big, very steric. So it always directs para. Another example of this is H2SO4, SO3. You can think of this as the sulfur variant of tert-butoxide, or sorry, tert-butyl, right? It's the same sort of branching substituent, right? Where we have three branches. So there's a carbon version and a sulfur version. Both of these very steric, and they always direct para as the major product. So this is the one thing that if you have to, if you have to ortho-para direct it, it always goes para, right? It's always going to go in the least steric position possible, okay? In that same line of thinking, right, let's say that I have a tert-butyl, which is a ortho-para director because it's alkyl. If I add an electrophile, again, this is always going to direct para. Always directs away, always. So it's forced to go in that position there, okay? So these are the steric considerations you would want to take into consideration. The sulfonation group, the reason why it doesn't matter too much for this one, where it directs electrophiles, is because it's a meta director, right? So electrophiles will always go meta. So not too big of a deal, right? That's always just where it's going to direct. It's not ortho, so nothing to worry about there. Okay, cool. So with that steric stuff in place, now let's talk about what happens when we have two directors on the same ring. How can we predict the product of that? It's pretty simple, right? You just have to take into consideration a couple of rules. So for example, let's say that I have something like this on the ring where I have an NO2 and I have a methoxy. In this case, right, always the first thing you want to look for is the strongest activator, right? Strongest activator will always beat everything else. So it'll be a weak activator, and it'll be any deactivator. Okay, so we have a methoxy, and then we have an NO2. NO2 is deactivating, it's I guess actually instead of activating, deactivating, let's not use those terms. Let's use orthopara. That's actually a bit better to use here. So orthopara versus weak orthopara. So like an alkyl group. So N beats O, but that beats R, and then any deactivator or meta director group, right? Actually, this would be like a halide as well, weak orthopara. And then any meta director, right? So methoxy's orthopara, NO2 is meta. So the methoxy is what's going to direct the electrophile. So we can either get reaction here, here, or here, orthopara to the methoxy group. We actually give it a color so we can see that this is the guy that won, right? Second general rule of thumb is try to avoid, or remember 3 is a crowd. Try to avoid putting 3 things together. That's just how I remember that very well. 3 is a crowd. So clearly not going to go there because putting that with crowd 3 things, right? All that's left now is this position and this position. If the electrophile is not bulky, then we can reasonably assume that both products are possible, right? For example, we will get both these here. If it is bulky, a bulky product or bulky electrophile like tert butyl, assume it goes para, right? That's probably the best bet. That's what, at least that's what I would put my money on. Okay, so you can always use strong orthopara beats weak orthopara beats a meta. I guess if you wanted to elaborate, right, this beats a weak meta, and this beats a strong meta. Right, so just the level of activation, that's what kind of determines this. Okay. One case where this may not be super clear though is, for example, this here. So in this case, we have an alkyl fighting with a halogen. In this case, right, both are about equal in direction. So maybe we might consider that can go in either of these 2 positions here. But remember, we can use 3 as a crowd as a sort of guideline or a sort of, voice in our head. Wait, 3 in a crowd is to tell us that sterics are bad, right? Look out for sterics. So is there anything here where sterics could be an issue? Yes, there is, right? This big bulky group here is a very steric. So if I add an electrophile, right, definitely going to go ortho to the bromine. Oops, sorry. Ortho to the bromine and not next to the tert butyl. Okay. On the other hand, let's say that we have right, let's say we have like a methyl and a actually, let's actually even do this. So sometimes people get really confused when they see rings attached to the benzene. Don't worry, the ring is no different from substituents. But I tell people, if this scares you, just break the ring. You can break it. So for example, let's say that I have like this here, I'm gonna break the ring. I'm gonna treat it as a methyl and a methoxy, and do my calculations or figure out my answer from there. That doesn't really change anything. Just look at the group that's on there that has an effect. So this oxygen, right, can have an effect, and this methyl can. Remember, strong orthopara beats weak orthopara, so oxygen wins again. So that's gonna direct here, here, and here. This spot is already occupied, so it's either ortho or para. Again, remember 3 is a crowd. So what we're going to get here is going to be the predominant product where it's para. Okay. Cool. Right. The ortho product is not gonna form at all. Right. It's gonna be very minor because it would do a 3 as a crowd type of deal. Okay. We could potentially have dueling oxygens, I guess, or we'd have like dueling donating groups. This would be a terrible one to have to guess though. So I hope this doesn't show up. Well, actually, no, this actually would cooperate. Actually, this is a foolproof one. They both direct here. So I guess if you had to direct, you probably go versus the nitrogen. But that would be kind of a nightmare. Let's see, what else can we pull out? Let's say we have something like this. Alkyls are weak donators, so people always try to think that they are going to lose to everyone, but they're still weak donators. They're donators, they're activators, they're orthopara directors, so they still will be NO2s. So this will still direct here and here. Let's say I put the NO2 over here, though. I guess it doesn't really change much, right? Because it just directs here, here, here. Never going to go here. Okay, cool. So for the most part, you're just kind of stacking your kind of odds, kind of stacking 2 things and looking at which one's better. Some of the foolproofs, again, like if I have 2 meta directors, they both direct this position here. If you have 2 meta orthopara directors, they both are directing to their orthopara position. So It kind of doesn't matter which one wins, right? Because they kind of direct the same positions. It's really the competition ones, right? The ones that compete that are a little tricky. Like, for example, this one here, right? It's a bit tricky. Let's say that I have this aldehyde here. Where could this possibly go, right? It could possibly go here, or it could go here. Again, if I kind of think about three as a crowd, actually, these are cooperating now that I think about it. They're actually cooperating completely, right? This is also going here and here. So you just think three is a crowd, and that will give you the answer, right? Sterix is a very good fallback if you're unsure where to go. Okay. So yeah, so that's the general thing there. The last thing to talk about are synthetic strategies. Actually, even before that, there's one last group we have to talk about that are kind of the weirdos. They kind of ruin everything for everyone. And those are the phenol and the aniline. Okay. So when it comes to phenol and aniline, right? So these OH and this NH2 here, these guys are what we call super reactors. They are incredibly reactive. If we just throw in bromine, we don't even need the Lewis acid. You just throw in bromine, these guys will overreact. So we will form the tribromophenol, and we will form the tribromoaniline 100% of the time. Absolutely hard to not get these guys to react. So if you do like a bromination, or like this could have been like a nitration, or I mean, sulfonation is not too bad of a deal, but it's still, you know, enough that, you know, kind of recommend against it. Always going to see some type of overreaction on these rings. Phenol you could actually stop though. So if you do this reaction in a non-polar, so this is Br2 if it's done in like water. If you do it in a non-polar, you can isolate the mono additions. So for example, a non-polar is like CS2. What is it called? Like CCl4. That's like a non-polar. Phenol is a little more controlled, right? It's not as donating as a nitrogen as the aniline. But we still do see problems with these guys in terms of their reactions, overreactions. If we try to do fatal crafts, right? Again, we don't really need the Lewis acid here, but it turns out, right, these guys are actually going to react a little different. So we don't need the, so for example, let's say that I have this here, right, the acylation. We don't really need the Lewis acid here. Actually, the Lewis acid would turn off the reaction because both the oxygen and the nitrogen would bond to the aluminum or the iron. And when they do that, they become positively charged, which, remember, if I have a cationic atom next to the ring, that's a withdrawing, it's a meta-director, and meta-directors do not accept Friedel-Crafts electrophiles. So usually do not do this with the Lewis acid on. But even if we get rid of it, actually, the lone pairs on the alcohol and on the amine are actually better nucleophiles than the ring itself. And so we always get acylation events on the oxygen and the nitrogen. So these guys are usually more willing to react than the ring itself. Also see this problem if we just do an alkylation too. In fact, alkylations with nitrogens go to completion. If I did, like, let's say the alkyl version of this, so instead I use this here, you'll get what we call the quaternary ammonium salt. It'll overreact that often. The phenol will just react once to make an ether. Okay, so these guys are incredibly annoying. You know, for the most part, they don't really do what you want. Even more annoying really is the nitrogen. Anilines, if you try to do any reaction in aniline in acid, so any of the H2SO4 dehydration reactions, right? So I'll put here electrophile. It actually turns out the major product of these reactions is the meta product. And that's because anilines are very basic, or relatively basic. They turn into NH3 plus or NR3 plus, which means that they're gonna, you know, act as meta directors. So aniline is definitely one of the worst to deal with. And this is a usually common trick question on the exams. Be aware of this. If nitrogen has a free lone pair, it will react with an acid, right? Whether it is this or it's, you know, these could be R groups as well. Okay. So what is the solution then to prevent these overreactions and prevent these horrible reactions? Actually, we kind of just saw it. What we tend to do is we take the phenol or we take the aniline and we do something called protect them. We protect them. So for example, oops, sorry, I kind of already drew it. I didn't mean to, but we can actually take that acyl chloride we used earlier and we can protect the phenol, or we can attenuate the phenol reactivity and the aniline reactivity, okay, by turning them into their ester and amides. So this here is an ester, and this here is an amide. Okay. If you kind of look here, the electrons can resonate into the oxygen, which makes it less likely to resonate into the ring, which turns down the activation of the ring, right? Makes them less powerful nucleophiles. So now when you do reactions like Br2, I mean, you will definitely need the Lewis acid now, but these are way more behaved. I mean, really I'll just make it generic here just to save time. Right? Any electrophile here, right? We'll get usually majority para product, but I'll also write here some, you'll get ortho too. I'm just drawing this note. I'm just drawing kind of two products on one just to kind of save time here. Okay, so we'll get these here. Yeah, so we'll get two products, right? One where it goes ortho, one where it goes para. Okay, and very easily the way to get rid of these groups is you just do NaOH, H2O. So hydrolysis, all it does is it cuts right here, cuts right there. So we get this here. So we can, I'll draw the aniline products, but it's almost as if you did the reaction of aniline without the protecting group. You got exactly what you wanted, but you did use a protecting group. Okay. Pesky little groups, right? The aniline, the phenol. So in synthesis, if you see it, I always recommend you protect it instantly. Just protect it. Just get out of the way. If you need to make an aniline, just protect it. It's not worth trying to do the reaction with just the aniline. You will lose points. We'll guarantee that to you. You will lose points if you try to do a reaction with just the aniline. Okay. Cool. All right. So with that, God, I mean, it's a long time, right? It took us 2 hours to do this. So hopefully you guys got some value out of that. I will also link videos that I made for 8B that are a bit better and less rushed if you guys need it, because I imagine this is truly like if you just need to get the material prepped in your brain, right? I definitely don't recommend this as your only source of understanding the material, because I did skip over a lot of things just so I could focus on the big three, right? Dienes, diels, alder, and these benzene reactions. Okay, cool. I wanted to go over synthetic strategies, but due to time, I don't want to spend more than another 30 minutes. Or really, I only want to spend like 50 minutes now just doing the exam, because we can talk about stuff anyways in the exam when we do it. So synthetic strategies, we'll have to wait until we get to the synthesis and we'll talk about it. But yeah, I mean, I imagine a lot of you guys are waiting for this, and I have been too, just to get to the exam. So let's go ahead and let's do the exam. Okay, cool. All right. So you probably looked at the exam and thought, wait, this looks nothing like the exam we did last time. I thought you would change it up. And that is true. I could have changed it up, but I like how this has a lot of practice on it. So I can write 3 exams, 4 exams with so much practice on it that you guys get enough practice, as much as you need, right? You have nothing to worry about. So cool. Format's going to stay the same, but the questions, right, for the most part are going to be what you're going to see on the exam. Cool. All right. So first question, right? Reactivity diels alder. Remember, dienes electron rich, right? So we want groups that will donate electrons. So when I look at these groups here, these atoms attached to the diene, I see a carbon with an alcohol. So this is inherently going to be withdrawing. So boo, we don't want that. Carbonyl is resonance withdrawing. So boo, we don't want that. All that's left now are these 2 nitrogen atoms, which do have lone pairs. So these guys are capable of donating in. Yay. Okay. But both are nitrogen. So is one better than the other? Remember, not only do we want donating groups, but we also want alkenes that will stay as, dienes that stay as cis. So this is going to be by far the best diene for diels alder. 100% going to react. Okay, cool. All right. You can imagine then that the worst one will be this one. This would be the best dienophile, right? So if I could get rid of this part here, this would be the best dienophile out of all of these. Just like if I got rid of these components here. Okay, cool. All right. Which hydrogen is the most acidic, and also rank them. So for this question, I mean, if you kind of look at it, you can just draw the anions. That could be a way to think about it, or at least begin the process of thinking about this problem. So I'll go ahead and get rid of these guys here. Okay. Again, we can think about what we talked about earlier with, conjugation. Conjugation is a great way to start this problem. Because if we look at one of these anions is not conjugated at all. Right, this guy is not conjugated whatsoever. So it might be, maybe the first thing we might do is put this at 4, right? And I already know some of you that are already had in the class and be like, oh, we'll actually just hold on, okay? I'm just saying that we could primarily just put this at 4 right now, Okay. When we look at these guys here, right, these are conjugated systems. And for the most part, I mean, we see that this here, 2 pi bonds, anion, that looks pretty good. This has 1 pi bond and anion. So one mistake that people make is they think, okay, pi bonds, more pi bonds we have, the better, right? And so they might think, okay, this must be 3 then, but then how do I choose between these guys? I'm a little stuck. So I implore you to look a little bit deeper into this guy and really into this guy and why this guy might be better. Again, we didn't get to go over this because I didn't have the time, but this is a ring. It's conjugated, presumably planar, and it has, looks like 1, 2, 3, 3 pairs of electrons, pi electrons, or 6 pi electrons total. This is an aromatic ring. So very commonly in these exams, these hydrogen acidity questions are actually disguised as aromaticity questions for you to recognize which anion is the most aromatic here. And so this here, the cyclopentadienyl anion, very, very aromatic, very, 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 very special, popular. And so this will actually be our most acidic because it goes from non-aromatic to aromatic, and aromaticity, very, very good. So this guy here that does have the pi bonds, right, 2 pi bonds, but is not fully conjugated, that's an sp3 center, right? See, this is sp3 here, right? This is going to be particularly stable, so we can put it at 2. So you might accidentally come to the conclusion that this is 3 because this here is 2. But if we kind of apply the same things, right? Ring, presumably planar, conjugated, but now it has 4 pi electrons. 4 is the anti-aromaticity number. And anti-aromaticity is the absolute worst thing you can have. And in fact, this is actually the least acidic of the protons. So again, you could have started with this as 4 just because it's not resonating, but non-resonating, non-aromatics are always better than anti-aromatics. Okay, this is anti-aromatic, this is aromatic, these are non-aromatics. Okay, cool. And so generally speaking, aromatics, so molecules that deprotonate into aromatics are the most acidic, and then the non-aromatics, and then the anti-aromatics. Okay, very important terminology, the way I said that. Molecules that deprotonate into aromatics are very acidic. So the fact that this guy deprotonated into an aromatic system is why it's so acidic. If it were already aromatic, so for example, if it were, right, like this pyrrole, sorry, yes, pyrrole. Pyrrole is already aromatic, right? It already has 6 electrons. Deprotonating this doesn't change that. So it's not like very, I mean, it is still acidic, but it's not hugely acidic because of that. Okay, cool. All right, halt there. Aromaticity, again, if you walk through the document, there's a couple of good tips. Biggest tip that I'll just say out loud is, you know, don't be afraid of these lone pairs that might show up on the outside of a ring. If you have an atom that looks sp2 with a lone pair, that lone pair is perpendicular or orthogonal to the system, right? So a way of visualizing that is if I kind of draw this planar. Wow, I'm trying to, good thing I'm not an artist, right? I'm just an organic chemist. If I try to draw this planar, right, the p orbitals will look like this, right? Only the pi bonds, right? Only the pi bonds are what we care about for aromaticity. The lone pair is going to be out here on the side. Kind of looks like a turtle. We have a little turtle here, our aromaticity turtle. Right. Anyways, this lone pair is going to be perpendicular to the system, right? It's not involved in the pi resonance. So when we're thinking about aromaticity, we're thinking about pi electrons, not these perpendicular electrons. So if an atom is already sp2, right, it's already pi bonded, it's already contributing electrons to the pi bond. These guys don't count. So this is essentially a benzene, so this is aromatic. Same thing here, right? So this is a pi bond in nitrogen, so it's already contributing electrons to the pi bond. So these here, right? And then so these here, these are not pi bonded, so these, I mean, these can resonate too, so these are definitely going to count. And then one of these oxygen atoms can count because that oxygen is not pi bonded. So 1, 2, 3, 4, that's 4 pairs, 8 electrons, that's going to be anti-aromatic. This might scare you, don't worry. Borane is isoelectronic to a carbocation, so actually I can actually redraw this such that this is just a carbocation here, that makes it easier to think about. But I can go ahead and now ask this question again. So once again, right, any pi bonded atom is not going to contribute its lone pair, so those lone pairs are not there. We're contributing the pi bonds, so these pi bonds here, pi bonds here. Cations do conjugate, but they are not pi bonds themselves, they don't have pi electrons themselves. So this is actually going to be empty, although it does conjugate. So the 6 electrons is going to be aromatic. Okay, and then this is a very special molecule. This is a non-aromatic molecule. It is a cyclooctatetraene. You need to know that this is anti-aromatic. Another example of a molecule you should just know is anti-aromatic is the following. Shoot, why am I messing this up? There we go. This molecule here. And at first sight, it may not be obvious why this is anti-aromatic, or sorry, non-aromatic, because it is, 10 electrons, which is the aromaticity number. The answer is because these two hydrogens here conflict if they're planar. So there's these two hydrogens here. And if this is a planar molecule, they're going to have steric interactions, right? They don't want to date, and yet we're forcing them to if they're planar. So this is also a non-aromatic that, is not very obvious unless you're told. Cool. All right. Again, I will post videos for this because I imagine, it's also good to just hear me say it or have a review on that. Cool. All right. Oh, wait, there's also the review sheet too. I forgot about that. There's the aromaticity review sheet. So you can look at that too. Cool. Which compound reacts fastest with methanol? And again, we can consider cations here because methanol means that we're doing SN1 type reactions. So just very quickly going to erase these. I apologize. I know I didn't erase it perfectly. So I apologize for those of you that care about stuff like that. I definitely do, but time's sake, right? And then consider the stability of the cations. We can see here we have an allyl cation. We have here also kind of an allyl, but I mean, think about this for a second. We have looks like a vinyl cation, and then we have just an sp3 cation. Okay. Remember, allyl cations are generally the best. Cations that are on carbons that look sp3 usually better than ones that are on vinyls. So we might instantly think that this vinyl is the worst if you remember that from 118A. So that's totally okay. When I think about the allyl versus this guy here, right? The allyl can resonate, this one can't. So maybe I give this like a 3 and a 2. And then we have this guy here. Again, it's conjugated, cyclic. You can see what's going on here. This is an anti-aromaticity problem, or this is an anti-aromatic molecule. It's an aromaticity problem. This has 1, 2, right? 1, 2. It's a 4 electrons, anti-aromatic system. This is actually going to be the worst. So if this ionizes, it forms an anti-aromatic molecule. So it's going to be the slowest out of all of them. So we can push all these up a number, 3, 2, and then 1. Okay, cool. A good version of this where it will speed up the reaction drastically is like a tropylium. Tropylium, when it ionizes, forms the cation here. But this is actually a trick question. And it's one that it shows up time to time. So it's good to know this. Aromatic cations are actually non-reactive because they form aromatic salts. So this is actually an aromatic salt. It is non-reactive. So despite the fact that you might think that the aromatic version of this is the fastest, it's actually not. Aromatic cations do not want to react. Kind of crazy to think about. They are super, I mean, I think there's a spiel about this in the book too. So this will actually be 4 also. This will also be the least reactive of all these because it's aromatic. It doesn't, why would the cation destroy itself, right? It wouldn't. So if it asks which one reacts the fastest, right? That's what we're looking at there, is that this would react still as 4. Forming the fastest would make this number 1. So if this forms the fastest, yes. So if it just forms the cation, yes. But reacting, it's also as non-reactive as an anti-aromatic. Yeah. So kind of an interesting problem that one is. Cool. All right. Moving on. Nomenclature, just look it up. You'll be fine. Cool. Predictive products. So just gonna get through this, right? Do as best as we can. Cool. So the first one we see here, we have a diene and we have an alkene. This is a diels alder. It's just kind of unraveled. Sometimes this will happen. And you just have to know how to draw this. The best advice I can give to drawing the diene in a way that's understandable is you want to draw the diene you normally would, and then just take note of stereochemical relationships. So for example, on this alkene here, right, the methoxy and the bond to the other alkene is trans. So we know that we want like this bond and this methoxy here to be trans to each other, right? That would be trans. This would be cis, right? Because it'd be cis to each other. So we know that this is going to be outside just for that reason. You do the same thing, or actually we don't have to because this is just on that inside carbon. So we just draw that in right there. Okay, cool. And then we can go ahead and draw the Dienephile as such, right? This is going to be a regiochemical diels alder, right? And a foolproof one of that because we have the oxygen donating to this carbon here, right? 1 sub donating opposite and then a 2 sub donating right next door. Okay, so this is foolproof. They're both going to do the same thing. So I can go ahead, I can draw my cyclohexene, right? Methyl goes on that sp2 carbon, no doubt about it. And then I can go ahead and draw my, because it's a one sub, we're going to have that ortho or right next to product. So I'm not at all stressed about that. Okay. Again, this here is probably my highest partial credit per answer. So probably, on the worst case scenario, 2 points, best case scenario, like 3 points, right? But if I want to elevate this question, I just have to include stereochemistry, right? And remember the outside endo rule, right? If a group is outside, it's going to be cis to the pi group on the dienophile. So the pi group is a wedge here, right? Then the diene outside group is also going to be a wedge. This is outside, right? This will be inside here, okay? And so this will give us dash stereochemistry as such. Okay. Oh, sorry, that's outside. What am I doing? That will give us wedge stereochemistry. I apologize. I'm losing it now. This is going to be racemic. Cool. All right. Oh, one thing I realized I forgot to mention: alkynes can also do diels alders. Completely forgot about that, mentioning that. I always forget this, especially because when I'm like running out of time. The only difference here is that instead of making a cyclohexene, you make a cyclohexadiene. So you're gonna make this. So stereochemistry is completely thrown out the window, honestly, because the dienophile no longer has stereochemistry. Yeah, so that's totally possible. Well, we forgot. Sometimes that shows up, so it's good to know. Cool. All right. NBS, that is a allylic radical halogenation. For these reactions, usually we want to go with the thermodynamics. So we can consider that there are 3 possible places for ionization or radicalization. Of these 3, this is a primary. These are secondary. So I'm going to go ahead and ignore this top one. All I have left are these 2 here. So I can just consider what the pi bond would look like if I just resonated it. So if I consider this one, it would look like that. And then if I consider this one, it would look like that. Okay. Because we're looking for thermodynamics, we're not concerned with the radical. It's very, very easy to think, kinetics, you get confused with kinetics. Generally speaking, with the NBS reactions, you want to go with thermodynamics. Okay. So when I think thermodynamically, right, whether I have this resonating set or this resonating set, the more thermodynamic pair is this one up here. So in fact, actually, what I'll get is just a single answer where the bromination is on this carbon here. Yeah. Cool. If you use that, you will be, as long as you think of thermodynamics, you'll be fine. Okay, you'll be totally fine. Okay. So for example, let's say that I have this here, right? And I do the allylic bromination, right? I'd have this radical and I'd have this radical, right? We want to go with this one. Oh, sorry, not that one. Sorry, this one up here. Down here, sorry. Right, for a thermodynamic product. So that's how the NBS reaction works. Always think about thermodynamics. The case where this would be different is if I did, let's say, like N-bule, right? N-bule, right, which is a base, it's going to steal a proton to form the allyl anion. Allyl anions are kinetically favored. Okay, anions like to be less sub. So we're going to actually form this anion here. So that's when you want to kind of reverse your idea, where we want to go with the less sub possible. Okay, so if I did N-bule, this is what I would form. And then again, I can like add things to it. So like, let's, for example, say I add an epoxide. That was a cool idea I mentioned. We can add an epoxide and then you can do some cool reactions where we add in like that, right? Just spitballing, right? Just thinking about things. Cool. All right. I know usually I tend to do like multiple questions. Just for the sake of time, I won't, but I'll still add some at the end of the key. So at the end of the key, I will still add some like, hey, here are some extra problems. Probably just only 1 or 2 of them, just to get your, just to increase the number of reactions that we have. Cool. All right. So again, we have 2 groups here. We have a bromine and we have an oxygen. Remember the 2 sort of guidelines here. One is that a strong ortho para will beat a weak one, right? Which will beat a weak meta, which will beat a strong meta, right? So oxygen and nitrogen are kind of the kings and queens of this section here. Although nitrogen does beat oxygen, then we have R and X, and then we have our meta directors, right? You guys have a chart, by the way, that tells you kind of all this information. NO3 is not tert-butyl, and it's not sulfuric acid. So first off, oxygen wins, right? Because oxygen is a stronger activator. So it goes here. NO3 is, or NO2, sorry, is not considered one of the bulky groups. So we can assume that it will go both ortho and para. Okay. Until we draw the ortho product, and what do we notice? What do we notice? We notice that 3 is a crowd. So definitely don't want to draw this one. Okay. So always draw both ortho and para, and then assess if there is anything that might, make you not want to draw one. Usually the case is you probably don't want to draw the ortho one. Okay. Now, very rarely do you sometimes get tri-subs, and you have to, I guess I didn't consider this. Sometimes you might get asked to do a tri-sub analysis, and that is totally possible. For example, maybe you're asked to do a tri-sub analysis here. In this case, the only place you could go is there, although go very, very reluctantly. So you could get an addition there of an electrophile. But tri-subs will almost always give one singular answer. And it takes usually just analysis of all the groups and what their effects are. For example, let's say that I have, this is a good one. Yeah, something like this, right? We're going to have a ketone, have a methyl, and have a methoxy. Again, the strongest activator is this guy here. So it either goes ortho or para. Definitely never going to this ortho position because methyl's already there. So it's a matter of ortho or para. If I look at the ortho addition, it'll make 4 as a crowd, or 4 is like a mob, right? So never going to go there. So obviously going to go on this para position. Okay, cool. So yeah, sometimes you'll get tri-subs. Just use your electronic effects, and for the most part, you'll be correct. Cool. All right, D is diene addition. We have HCl at 0C, so that's a kinetic condition. So again, you can use the trick that I highlighted where you kind of talk about 1 sub versus like if it's a 1,4 or a 2,3 type carbon, or you can just draw all the cations if you want to. I will, just for the sake of this video, just draw out both possible, initial additions. And it's up to you. I mean, I'll leave it up to you guys if you want to resonate or not. But actually, I guess whatever. It takes less than a second, right? So we get this, and then we get this here. Right. And so you can clearly see, right, the tertiary cations in the bottom set. So this is the set that we care about the most, right? The kinetic cation is clearly the that cation there. So for this class, we can go ahead and capture on that cation, right? Remember, if this is a D here, so this is DCl, you'll have to draw in the deuterium that added on the 1 position here. But that's okay. I think most of you guys are fine with that. And then remember, deuterium was not hydrogen, so if we do form a chiral center, we do have to indicate that. This would actually be a mess. Technically, there are 2 products here with their own respective chiral enantiomer. So there's a lot of stereoisomers here. I'll just say that right now, because you don't know if D and C will add cis. You don't know if they add trans, syn, or anti to each other. And then you don't know if they add as wedges or dashes. So 4 products total. I just don't want to draw them out. Cool. All right. E, I kind of mentioned this one, but I'll be a bit more clear here. This zinc reaction we used when I mentioned you can do a Friedel-Crafts, and then you can deoxygenate the carbonyl to get that linear form. Usually this is restricted to aromatic carbonyls or aromatic ketones, so ketones that are conjugated to benzene rings. So you can see what the point of this reaction was to kind of elucidate or kind of make you think about that. But the other thing here that I'll talk about very briefly is, because we'll talk about it in synthesis anyways, is that it also allows you to turn what is a meta director to an ortho-para director. So we'll talk about this a little bit, what I call chemical chameleons. You can do reactions with a certain form of a chemical chameleon, then convert that chameleon into its other form and kind of trick people. For example, let's say that I have this an NH2 here, and I have an alkyl chain here. Both of these are ortho-para directors. And so you might look at this and think, this is a trick question or a typo. Something is wrong here. It takes a little bit courage and a little bit of knowledge to know, oh, wait a minute. If these guys are ortho-para directors, but they are meta-directed, they must have been added together as their chameleons, right? And so actually NO2 also, NH2 is also another chemical chameleon. And so we can go back to their meta-directed forms and think, oh, okay, now these are meta-directors. Makes more sense how these things were added. Okay, so chemical chameleons, biggest thing in synthesis is that idea. Cool. This here, we kind of just saw it earlier, right? We have a strong base. We have cyclopentadiene, right? That hydrogen there is acidic because it forms aromatic anion. Oh, cool, right? Aromatic anion. So if it has a possibility of forming an aromatic, aromatic ring, it's definitely going to be incredibly acidic. Cyclopentadiene clocks in at 15, which is even more acidic than an allyl normally, right? So it's pretty low down there. Okay, cool. Only way this wouldn't work, so it's an example is that wouldn't work is if it were like tropylium or something, where this hydrogen, if I removed it, would form in it would result in an anion that is anti-aromatic. So this would be an NR. I try to do this one. Okay, cool. I have a diene, I just have heat. So you might be looking at this and thinking, what in the world is going on? Looks like looks like nothing's happening here. This is our electrocyclics that I didn't get to go over. Here is the general spiel on this. Okay, cyclobutene can open up in heat or in light into butadiene via electrocyclic process. And you can go backwards in light, so you can close this in light. However, you cannot go backwards in heat. So the reverse in heat is forbidden, but you can go back with light. So think of heat as a thermodynamic condition, right? It's thermodynamically favorable for a square to open up because squares hate being squares, but it's not thermodynamically favorable for a chain to become a square again, right? I mean, we don't normally make squares in this class, so we should, we don't have a really easy way of making it. HV is sort of like a forcing condition. It forces it to close. So it's sort of like a, like a gun to the forehead to the butadiene, like you gotta close up. You gotta close up, right? So HV is like sort of the, kind of forces it out of that thermodynamics, okay? Same thing with trienes. Trienes, for the most part, prefer to be closed because they're conjugated into a ring. So thermodynamically, they sit on the ring side. You can close them usually with, open them usually with heat, but it's, again, not thermodynamically favored. But you can also, do HV. You can also just light it, throw some light at it. I actually have this like nice picture. I might show you guys of a light reaction that I did, if I can remember to send it. Okay, cool. So there you have it. That's just the spiel there. You guys did not do any sort of stereochemistry, so you just need to understand this idea that they can open and close, stuff like that. So this will be NR, right? Because this would not thermodynamically go to the thing there. But if I used HV here, it would close up. But you don't need to know the stereochemistry of the methyls if it did. Cool. All right. H, we have a bromine and a tert-butyl. We talked about this. Both are equal in direction, so you might think that it goes in both spots, but tert-butyl is so bulky, right? Ain't no way we're getting that chlorine next to that. Okay, so we can go there. Cool. All right. Moving on to the mechanism, we have a CF3. Again, CF3 is a meta-director, so make the electrophile however you want to, right? Or make it with, dehydrating it. I'll just do this very quickly. Just make sure that when you do the attack, you do it on the meta position. So CF3 is here, NO2 will be here. Oops, sorry, I drew the wrong cation. I was thinking of the 118C class for a second. So make your dehydrate this, make the NO2. You'll form this cation here. This can resonate, blah, blah, blah. But eventually, right, this H gets taken off. Be sure to draw the resonance forms. Again, I've already passed the class. I can do whatever I want. So once you guys pass, you guys can do the same thing where you skip intermediates. Just make sure to get that meta portion in there. Okay, cool. All right. Moving on to synthesis now. Again, usually the benzene synthesis people love because, again, it's all rules. So as long as you know the rules, you'll be fine. So usually people do very well on that. Sometimes there is a chapter 14 related synthesis, like a diels alder or some kind of like allylic type transformation. This is actually what's going on here. If you look here, we're going from no rings to all rings. So we're going to hexane to benzene. So how in the world could we possibly do that? Well, we can trace back the NO2 just to a benzene, right? So that's just NO3, H2SO4. And now we just got to go back to thinking about, how can we make alkenes, right? How can we normally make alkenes in this class? Maybe we might even think about what might be the first reaction we might even do here, right? If I just want to make an alkene, all I'm doing is an elimination. So I can think about having a bromine here and doing like a butyl, elimination. Well, look at that. That bromine is allylic to this pi bond. So possibly what I'm just doing is an allylic bromination. So all I'm doing is NBS, HV, and then, okay, well, if I wanted to make that alkene, okay, maybe I just do this. And then maybe I just go back to this. Right? And then maybe I just go back to this. So this is just a cheeky little problem. Just highlighting that, allylic chemistry does allow you now to make benzenes. Although you would never really do this, right? Like no one would actually spend this time doing this. But you can brominate and you can NBS, bulky base, NBS, bulky base, NBS, bulky base, and then the nitrate. Okay. Cool. So it's cool stuff you can do there. From here, you could make like a Grignard, right? And do other stuff, like not benzene related stuff. So maybe you make a Grignard and then, you add things like carbonyls. This is also a very popular type of question. You'll see, stuff like that. So Mg, and then in this case, this aldehyde here. Sorry, I know my handwriting is really bad. That's why I try to enunciate everything that I say so that you guys can at least hear me say it. Okay, cool. So something like that. Cool. All right. So cool little benzene problem there. Again, either you get a synthesis that's chapter 14 related, so something allylic or something Diels-Alder related. The next midterm has like a Diels-Alder type reaction thing. Or you get a straight up benzene question where you have to throw things onto a benzene, okay? Now, this one I chose for a lot of reasons because it has a lot of the core concepts right immediately there, so we can talk about them now, okay? Remember, when we think about benzene reactions, there are rules how things go. For example, certain groups direct certain groups, certain groups direct groups to a certain position. So one of the first things you can look at is just how things are directed, right? I notice here everything is meta-directed. So because everything is meta, I would expect there to be some meta director that did all these directions. But when I look at these guys, right, they're all ortho pair directors. We have NH2 with the lone pair, we have alkyl chain, we have chlorine with the lone pair, right? These are all ortho pair directors. So maybe you might think this is a typo, right? You may think, oh, maybe what you meant to do was put the NH2 here, right? In that case, yeah, right. Then obviously NH2 is ortho pair directing and it directed everything where it's supposed to go. But in fact, this is not a typo. Because again, if it's impossible for your current group to do what you did, possibly we have a chemical chameleon on the loose, okay? And so those chemical chameleons are NH2 and this carbon chain here. Remember, if we have a linear chain, right, the only way to have a linear chain on a benzene ring is to go through a carbonyl, right? So we can have a carbonyl as such, and then NH2 could have been NO2, right? And so the way you reduce both of these, you would use something like, you can use zinc, you can use the Clemmensen reduction. It will hit both the carbonyl and the NO2. It's not avoidable. And again, now you have these two meta directors that could have coincided, they could have cooperated to add that chlorine. Okay, so we get back to here. Cool. So we get this here. All right, now we have two meta directors, NO2 and the acyl group. And again, both of these we can add from a benzene ring, but this goes back to a cardinal rule, right? Let's say that I acylated here. So I say, okay, maybe what I did was I acylated AlCl3 and then H3O plus, right? And what I had here was an NO2. I broke the cardinal rule of Friedel-Crafts reactions in general. Friedel-Crafts will never occur on meta-directing rings, okay? So if you do make this mistake, unfortunately, you will lose a lot of points, okay? They're not merciful on this. And so whenever you have a Friedel-Crafts, I always recommend trying to do it first. Try to get it out of the way because it has the limitation, right? That it will not go on a meta-directing ring. So get it out of the way, right? Get it done. You can do this, and then you can don't forget the H plus workup. And then you can do HNO3, H2SO4, right? This is acceptable, right? You can get that meta relationship, just do the acylation first. If I do the nitration first, reaction's not going to work. You lose all your points on synthesis. Okay, cool. So a lot of things, pulled out in this one. Again, main point is look at the final product, look at the relationships. If things don't make sense, consider chemical chameleon. For example, let's say the last possible thing that I have is this here, right? I have a ketone and an NO2. that are, and I have the Cl here, right? I have these groups here that are kind of oddly paired against each other, right? I have a chlorine that could have directed the NO2, but in no way could have directed this, this ketone meta, right? I have a ketone that could have directed this chlorine, but could never direct this NO2. And then I have an NO2 that will never direct this thing ortho or para. So I have groups that don't really, work out with, I don't have one group that kind of has everything arranged around it nicely. So maybe I consider chemical chameleon. Okay. Chemical chameleon in this case would mean that I have like an NH2, for example, and I have this here. And so, suddenly things are starting to make a lot more sense, right? This NH2 has everything ortho paired to it. So I can see that it would definitely, do the reactions I want to do. Now, to turn NH2 into NO2, you just use MCPBA. You just use an oxidant. And remember, anytime you have an NH2, an aniline, consider that it was protected, because if it isn't, it's going to do everything you don't want it to do. So I can consider that possibly there was a protecting group and I removed it with just a hydrolysis, right? Something like that. And then I can kind of remove these groups one at a time, right? This is kind of a counterintuitive thought, but it should make sense when you think about it. When you are removing things ortho and para from a group, just keep in mind that the last group added would probably be ortho. So it's more likely that the chlorine was added last, because again, the first group that's going to go on an ortho para director in major quantities, 60% of the time is going to be para. Okay, so it's much more likely that this acyl group was added para first, and then chlorine was added afterwards. Okay, but from here, right? Sorry, I meant to write this here, so I'm just going to kind of jot these down very quickly. But we can do this, and then we can get rid of the acyl group, right? We could just say that the acyl group was added to the nitrogen. Sorry, like this. And then how do we make nitrogens? We make them from the reduction of NO2s. So this is a bit of a long one. 1, 2, 3, 4, 5, 6. This is not something you would expect on an exam. It's a little too long, but I mean, the more that we can work backwards, the more that we can see where we could potentially start and where we could potentially end. Okay, so we get to this point here, right? So we can do right, NO2 plus cation, reduce it into an aniline, protect the aniline, and then do our two reactions. First, the para reaction, then the ortho reaction, and then get rid of the protecting group, and then oxidize back into the NO2. Okay, cool. All right. Now, because we do have a little bit of time, I will go over one last one that's really important to know, just because it is the first video and it doesn't hurt to have this. The last transformation that's really good to know is how to have an ortho substituted ring as just ortho substituted. So remember, most things will go para first. So how in the world did I get this chlorine here with nothing at this position here? It's actually very simple. I'm going to just move ahead in time a little bit. So remember the sequence: NO2 into NH2 into protected aniline. What you can use is the sulfonation group. So I mentioned this before very briefly, but we can add and subtract sulfuric acid groups from the ring, right? When we add them, they will always go para because they're so bulky. And this acts as a para blocking group. So it blocks the para position so that I can do a chlorination reaction or whatever electrophile reaction I want to do to go ortho, right? And then I can remove this group out, right, with a hydrolysis. Now, I will just add this in just to remind you guys, but if you do like a D plus D2O, right, in heat, right, that just means that you're adding a deuterium there. So I'm just adding just extra knowledge to your brain here for a second. But in the case of this problem, right, if we use H plus, it'll just be H. Okay, but that's how you can get, right, a ring that's ortho substituted with absolutely nothing para. Because remember, ortho para directors always want to direct para first. And that's totally possible that they can. But sometimes we don't want anything para. We just want something ortho. And the way we do is with this para blocking technique. Number one thing people mess up all the time is people try to para block on meta director rings. Just keep in mind that if I sulfonated this ring, that's going to go meta. Okay, meta directors direct meta. You do not para block. Okay, and also again, keep in mind that aniline is not very compatible with acid. So don't try to do a sulfonation from here, because sulfonation or even nitration from here, let's say I do a nitration, that's going to go meta without the protection. Okay, cool. All right. And I apologize, I'm speeding through this just because, you know, so much time. I mean, this wrapping up at 3 hours and I didn't want to do that. So I'm sorry. Cool. You know, I'm realizing now I should have just sent the videos. I have some 8V videos that I made last quarter that I could have, they're good enough, I would say. So I will still do that. If any of you want to skip the first part, I'll write it in. Cool. All right. NMR. Told you guys, didn't I tell you guys that if you just literally wiped your ass on this section of the paper, they will give you like partial credit for it and then end up giving full credit for it, because that's just what ends up happening with NMR. So please, if there's anything that I want you guys to take away from this, please, 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 please just pray to your God that you just get most of the partial credit. Don't do anything more. Don't waste your time. It's not worth it. But usually the NMRs in this section are benzene related. You can quickly check by looking right here, 6 to 8. Usually if there's activity, you can figure it out. 3 general patterns you want to know. These are what I call the twin towers because they're 2H doublet, 2H tublet, so they're twins and they're towers. And so when you see this, you know that it is going to be what we call a para-substituted diene, or sorry, a benzene. So this here, right? That's pretty simple if you see that. Meta, you'll see it on the other exams. There's a meta example, usually has some kind of distinctive singlet in it. So meta will usually be, yeah, some kind of distinctive singlet because of this H here. So this H is matching this here. And then ortho is usually just a mess. It looks like tall grass, like just a bunch of like no twin towers, obviously, and no clear singlet. Okay. Sometimes you might get a trisub. Trisubs are actually very easy. It's just 3 singlets just like that. Okay. And the only way to do 3 singlets is, you know, if it's trisub like that. Okay, cool. So, I mean, this one is clearly going to be the twin towers. Okay. I can quickly just do some DOU work just to make sure that's the only unsaturation. So 9 times 2 is 18 plus 2 is 20. 20 minus 12 is 8 divided by 2 is 4. And benzene is 4. So there you go. That's all my unsaturations. I see a broad singlet that's really high up. So if it's a broad singlet, it's going to be an OH or an NH. See an O. So I know there's an OH. The fact that it's really high up, remember the cutoff here is when it's sp2 based versus sp3 based. So if this were an alcohol as such, it would be down here, right? But the fact that it's all the way up here at 9 tells me it's unsaturated. It's all the way up here. It's unsaturated all the way up there. So it's going to be actually a phenol. It's next to the ring. It's conjugated, right? That conjugation is what's driving. See, this is, if you kind of draw the resonance form, this is going to be positive. So it's driving the alcohol to be, this proton to be very acidic and very positive. But yeah, so this is going to be this. And then we have something here. Clearly, the rest of these are then just going to be on here. Damn, I typoed. This is 3H. I'm stupid. Should be just that. Cool, right? So the 2H triplet that's right next to the ring up at 2.5. The 2H multiplet that's a little close to the ring, not fully there. And then what should have been 3H triplet because I was copy and pasting and not paying attention, right? That there. Cool. All right, so very easy. You can see here, usually what you'll see for benzenes is a band, like around here, like of 6 carbons, you usually see like a band. I think of it as a barcode, the benzene barcode is what I call it. But you'll see that sometimes. In this case, you kind of do see it, right? 1, 2, 3, 4, 5, 6. So it is kind of banding, but not as much as you normally would see. Cool. All right, with that, that's the midterm. That's the first midterm. I'll get the second one out tomorrow. Again, I apologize for all the rushing that I did. I will definitely include videos for the benzene portion and the aromaticity portion that can help out in understanding those. Okay, cool. All right, see you guys later. Let me know if there's any questions or anything.